Hey there! So today we're going to be doing challenge set 2 from Cryptopals, and just like the last video, I've looked through the challenges, but we're going to be writing them like kind of live coding style. So I'm going to write them up as we get to them. The goal of this video, this whole series, I'm going to try and do them all, is it's kind of aimed. I know people use these challenges as a way to learn cryptography and or learn programming, so I'm doing these in Python 3. I'm like not any kind of coding expert or cryptography expert even, but I feel like I know both sort of well enough that if you are trying to learn either one, that I have something to offer, hopefully. Hopefully you get something out of this, but that's kind of who it's aimed at. And I've changed up the video format. I'm doing like 1080p and I'm trying to make everything bigger. I don't know if the last one was like hard to read or not. If you are someone who's actually watching this, especially if you're someone who watched the first one, which that's cool, you came back. Like I'm surprised anyone even watched the first one. If you can leave a comment, like, I don't know, is it readable? Like, it's hard for me to tell because I pretty much do everything on my desktop. So I don't know if people watch these on mobile or what. So it'd be nice to know if I'm gonna put time into making these, if like it's even viewable. And yeah, I guess with all that rambling out of the way, let's go ahead and jump into these. So the first challenge, we're going to be implementing PKCS number 7 padding, which I think I talked about this a little bit in the last one, but basically the way it works is in AES, well, so you could pad anything, but I'm going to talk about it in terms of AES. Everything has to be a full block. So you have to pad stuff to make sure that what you're encrypting or decrypting, well, you don't pad ciphertext, but you have to pad it before you encrypt it so that it's exactly this full blocks is what you're putting into AES. So PKCS number 7, the way that works is however many bytes it takes to fill a block, you get that many bytes of that byte value. So like in the example here, they want to pad to 20 bytes, and Yellow Submarine is 16 bytes long, so we're 4 bytes short of 20, so we need 4 bytes of the byte value 4. So if we were 5 short, there'd be 5 bytes of XO5. And padding is mandatory, so even if your plain text was exactly, filled out blocks exactly, then what it would do, it would add an entire block of padding. So in the case of AES, there'd be a 16 byte block that was just 16 bytes of the byte value 16. So I don't know, hopefully that makes sense. And I don't know why they're having us, because you can pad anything, right? But all these challenges we're doing are going to be AES, at least in this set. And AES is always 16 bytes, but we're going to go ahead and implement it not as just a function in this like challenge number 9. We're going to create our own padding module, since padding is something we're going to be doing a lot of. So we are going to create a padding. And so what we're going to want to be able to do is pad something, and then we're going to want to be able to unpad it. So pad, we're going to have our plain text. We'll take everything in bytes. We will need to have a block size, what we're padding to, and we will return bytes. And then unpad will be the same. We're going to take I guess at that point it's not a ciphertext. Let's just, here, we'll just call these, actually, let's just do data. Bytes, block size, and we're going to return bytes. So now in our padding, or in our pad, we want to know how many bytes it's going to take to fill up the last block, because we need it to be, the plain text needs to be a multiple of the block size. So we need to know how much data we have modulo the block size. So like in the example of, let's say we're sending something that's 20 bytes long to AES. Well, the AES block size is 16 bytes, so we're going to be 4 bytes over. So 20 modulo 16 would be 4. If you're not familiar with modulo, it's basically, you can think of it as just divide and take the remainder. So 20 divided by 16, the remainder is 4. So that tells us this will tell us how many bytes into the last block we are. And what we need to do then is subtract that from the block size. And that will tell us, and I think, or order operations, I think it should do modulo length of data and then do subtraction, but just for clarity and also because I'm not entirely sure, we'll wrap it in parentheses. So this will tell us now how much padding we need. And it works out too that there'll always be padding, right? If our length of data, say we passed in 32 bytes, modulo a block size of 16 would be 0, but we always, padding's mandatory, so then we would have 16 minus 0, so we still will have a whole block of 16. And we'll just call that padding. And then what we want to do is we want to take our data and we want to add to it. This right now is an integer. So it's an integer that tells us how much padding we need. And remember, PKCS7 is that integer that many times, but in bytes. So we want to turn that into bytes. And then we want that many of them. So this should take that byte, make a byte string that many bytes long, and then append it to the data, which is what we want. And then when we unpad something, let's see, we'll need to know how long it is. Actually, here, I'm going to call this padded. And then actually, just because it's gonna bug me, let's go ahead and call it plain text, because that is what we are padding, is plain text. Okay. And then let's go ahead and we'll do some error checking, because we want to make sure. So if length is not, actually it's so I keep doing 16 because I'm thinking about it in terms of AES, and AES is always a 16 byte, but we're padding to anything. So if the length modulo the block size does not equal 0, that means if it, actually I could just do this. So if length modulo block size isn't 0, so we could actually do the same thing of just if length modulo block size, or maybe I should keep it the other way for code clarity, but I don't know, I think once you get used to coding, or used to like the Booleans, you'll see a lot of it without that because you don't need it. But so basically, Python evaluates 0 as false and anything else is true. So if length, we're going to take whatever the length modulo the block size is, and if it's 0, then this won't happen, and we don't want it to happen because we want this to always be 0. And if it's not 0, that means this will evaluate to true, and we're going to raise a value error that the input data is not padded. because everything has to be, if it was padded and encrypted, it had to have been divisible, evenly divisible by the block size. And then we want to also check, we're going to have another function. We're going to have if it's not, we'll call it valid padded. So we're going to check and make sure there's actually valid padding before we try and unpad it. And if it's not valid padding, then we will raise a value error. I don't know, let's just say not valid padding. And then if all that works out, now we can unpad it. So remember, our padding is, we're just going to look at the very last byte, because that'll tell us, remember, because all the padding is the same byte value. So we'll look at the very last one, and then what we'll do is we will slice off that many from the end of padded. So we're going to get the last byte of our padded, and then we're going to make that, so say it's like in the case what I was talking about, say there's 12 bytes of padding because we passed in a 20 byte into a 16 byte block size. So the last byte will be 12, and then we'll use the string slicing. We'll go from the beginning to -12, which would be 12 bytes from the end. So basically we're going to take padded and return everything but the last 12 bytes, or in the case of different values, it'll work out. So then now all we need to do is write our. So I'm underscoring these. I don't remember if I talked about this last time, but the underscore is basically just Python's convention for saying that it's like a private method. So which is weird because Python doesn't have public and private methods. So it doesn't really matter, but it's kind of just convention to alert anyone reading the code that this is not a function you're calling from basically outside this little package. It's basically just a helper function. So is valid padding, we're going to take padded bytes and we're going to return a Boolean true or false. So we want to get the last, whatever the last byte is, just like before. And now we want to make sure that the last, however many long that is, they're all that value. So we can, the string we were going to want to compare it to is just like how we did it before up here. We're going to do that here with, so we're going to get that value, whatever byte value that is, and we're going to do it that many times. And we want to take the end of our string. So this here would be the beginning, like, right, we're whacking off the end. Now we're going to do the same thing, but start at that value because we only want the end. So we're going to return padded. That's the part of the string we want is the negative of that value. Like we're going to start, if it's negative, say in the case of the example I've been using where there's 12 bytes of padding, we're going to start at the -12, which would be 12 bytes from the end. And then we're going to go all the way to the end. And we want to make sure, or we want to compare that to what we know valid padding would be. So this should be good. I guess here actually technically, so we're only using length in one spot. So we can just, there's no sense in that, having a line and setting a variable, because that's the only place we're calling it. And this should be good. So we will, save that. And then now go back to, I'll actually do our challenge 9 now. So we're going to no, so from utils padding, let's import pad and unpad. And then we'll do our if name main stuff. And again, so I'm, excuse me, I'm kind of aiming these videos towards people who are trying to learn, but I'm also like, I would not be anywhere remotely close to the best resource to, like, if you're really, really trying to learn, like just from the absolute beginning, like you don't know Python at all. There's like just so many really, really good and well put together resources on how to actually learn programming and like the fundamentals of programming and all that in general. So I'm not going to go over like, you know, what functions are and how iteration is and, or, you know, what any of this stuff is. But that said, I'm still trying to aim this at helping people who are unfamiliar with Python. So hopefully I kind of pull that off. So in our, what are we trying to do again? So they want us to pad this to 20 bytes, and we're going to do like we did. Actually, let me cover this one. We're going to do like we did in the first video. So our example is and we want the answer to be that, and our result will be, so yeah, I'm not writing tests or anything, but we'll just do a kind of our cheesy print statement test. Our result will be, if we pad the example, and we'll print out do we get correct? We'll compare the answer to the result, and we'll go ahead and print out the result. So we have something to look at in case we got it wrong. And then we'll go ahead and we padded it. Now let's unpad it. And we'll see if we got that one right too. And we'll compare result to example this time. And we'll print out example again. Oh, I was like, why is it not highlighting correctly? So also again, like I'm not using an IDE. Mostly because like I said, I'm not like a Python expert or anything, and I've been trying to learn Python, and I find that when I'm trying to learn a language, if I use an IDE, like I get lazy, and it just, because it's, you know, so helpful, that I end up like I don't remember things as well, and then like I get in a situation where then I cannot write anything in that. I can't write any code in that language unless I'm sitting in front of the IDE. So when I'm trying to get good at a language or something, I don't use an IDE. So that's why I'm just using like Sublime Text. I mean, that's just me. Do whatever works best for you, but this is why I probably should use an IDE because it would make it smoother for the video, but this is kind of just what I'm used to for Python at least. So that should be good. And let's see what happens when we run it. Oops. Challenge 9. Oh, we did not pad it. We didn't give it a block size. So we're padding it. The example, they wanted it to 20. Okay. What did I do wrong? So we correctly padded it, but then we padded something that was, oh, that's why. So it's a good example, though. It'll show you what happens when you give it something that's a full block size, is it pads a full block's worth of that. So it padded 20 bytes of the byte value 20. So this is in hex, so that's 116 plus 4, so that's 20. Because what I did was I padded the result, which was already something that was padded, and what I wanted to do was unpad the result. And there we go. Now it works out. So now we can go on to challenge 10, which is implementing CBC mode. So we looked a little bit at ECB in the last one, and we're gonna, I want to show you kind of how CBC mode. Show you how it works, and we'll see why we want, basically why we don't want ECB. So I think I showed this last time, where basically ECB is we're taking a block, we're encrypting it, and we're returning a block. So every time you use the same block, with the same key, you'll always get the same ciphertext. So that's how we found we were pretty sure that's the challenge the last challenge we did. Challenge 8 was, yeah, detect AES. That's how we detected ECB, is we gave it a bunch of the same thing to decrypt, and we checked for duplicate blocks. So and then I think I showed this kind of like famous picture. This is why ECB is not very good, because it doesn't, like when you encrypt that, right, all of these are everything that's white is the same block. Everything that's black is the same block. So you end up being able to get information out of it. Well, CBC attempts to fix that, where now every block of plain text gets XORed with the previous block of ciphertext. So it's just a way to like mix it up. And the very first block, since there is no previous block of ciphertext, you use an initialization vector. And typically your initialization vector should be random, or at least should increment. That way, every time, so even if we did, so like if you use the same initialization vector every time and encrypted something, you would always get the same thing back, because it would end up working out the same. But by using a different initialization vector each time, it's XORed here, and then what you get out is different, and then that propagates all the way down the chain. Like you change one byte anywhere previously, and then everything after that is going to be like completely different. So it's just kind of a way to not end up with something like this, and instead end up with something like this. And then decryption is obviously the reverse, where we're encrypt the ciphertext, and then we're going to take what comes out, we XOR it with the previous one to get back the original plain text. Hopefully that makes sense. And so what we're going to do here, so they want us to build up, so like how we kind of did ECB last time, I'm pretty sure I remember that's how we did it, where we sort of wrote our own ECB, but using the PyCrypto ECB. So kind of what I feel like they want us to do, and what I'm just going to go ahead and do, is we're going to kind of make AES ourselves, but we're not going to like make it from scratch, where we're going to sort of like have to actually figure out how the internals of AES work. Excuse me. How the internals of AES work, and then like, you know, create it from that. We're going to use the PyCrypto AES ECB mode and have it just do single blocks, and we'll use that kind of like as our sort of primitive, and we'll make our own AES out of that. So basically we're going to use PyCrypto to do all the actual everything that happens in here that we don't know how to do. We can think of it as just a black box we don't know how to do, but we'll use that to encrypt single blocks, and then from that we'll build out the CBC mode and ECB mode, and they'll probably want us doing other modes, which I don't know. Once you've kind of built it out, it seems sort of meh to keep using our thing, because once you build it, then it's just sort of an abstraction, and we're just going to call it and not be thinking about it anymore. So I don't know how much you get out of that, but it kind of seems like that's what they want us to do, and it'll be helpful to see how to do it. So basically, that's just a long way of me saying that's what we're gonna do. That's what we're gonna do. So we're going to create an AES module, and I'm gonna kind of make it the same way I would. We'll use it the same way like how PyCryptos is. So I'm gonna try and do it so that you'd call it the same way and the variables are the same, because that'll just make it both easiest to think about later on, because PyCrypto is what you will use. PyCryptoDome is what you'll use when doing cryptography stuff, or at least like CTF challenges and stuff in Python. So we're going to sort of model it like how we would that. So just like the PyCryptoDome AES, we're not going to do any sort of padding inside. Like we're just encrypting. We're also going to have it be where, so we're going to have sort of like, and I think you do the same convention for classes as well, where we're not actually directly going to call our classes is going to do all this. We are going to do like how PyCrypto does, where it has a new function, and what that new function does. So you give it in here, you'd give it your key and your mode and your IV and all that. And then in here it returns the AES. That way, if we change anything in here, or we change whatever the internals are of this class, or how we want to handle the abstraction of doing AES, it doesn't really, all we have to do is just change the function we're called. We return something different, or we can, I don't know, it's just an easier way to sort of like manage all that. But we'll be doing XORing, because as we know now, CBC mode, we're XORing with previous blocks. So we'll need to use our padding that we built. That right now, so one of the reasons I separated padding is because I imagine later on maybe they'll want us implementing other kinds of padding, and then we'll still be able to handle that with our padding. But right now, since all padding does is private key, whatever, PCKS. Yeah, wait. What does it even stand for? Public key cryptography. This is gonna bug me now. Public key cryptography standard. Okay, so I always mix up the C and the K. P, but it's easy to remember if you remember public key, PK. Anyway, random side divergent there. So we're gonna want our padding from utils padding. We're not gonna be unpadding anything. So but we will need to pad stuff. No, sorry. I just got done saying we're not gonna use padding at all. But we need our XOR, and that's in utils XOR. Man, I don't know what it is about like just doing a recording, knowing that like whatever I say is like final and on there, just makes my brain not work as good. It's like so much more focus. It's weird. And then we're going to use the same sort of variables that the AES module in PyCryptoDome does, where it's a block size. And I don't know why we have a variable for this, because AES is always 16 blocks. And then we had mode ECB. I believe that is 1 on theirs as well. And then we have CBC. And then, so what our AES then, we'll have, when we initialize it, what we'll have is a key in bytes. Again, we're doing everything in bytes. We'll have our mode as an integer, and then our IV is also going to be bytes. And then let's go ahead and do a little bit of just error checking. So we'll make sure that the key we get is instance. Is instance. We'll make sure, this is a way to check. We want to make sure that our key is bytes. So it'll tell us whether or not key is bytes and the length of that key. Now AES, every block is 16 bytes, but you can actually have different size keys. So like when you see AES 128, AES 192, AES 256, I think those are the three. That's not a difference in block size, that's what the key is. So maybe I shouldn't have this check here hard-coded because you can have different keys, but for right now, maybe we'll have to change that, but right now we're just gonna leave it like that. So here's the other thing I should say, because I kind of decided what we were gonna do was take from crypto cipher import. So the way we would normally want to use the AES, we would report it as AES, but I don't want to call it that because then it might get confusing in our code. But I don't also can't call it that because we're conflicting here. So I will call it, since it's the primitive we're kind of building up our structure around, let's call it AES primitive. So here we'll create it. So this, normally we would say like import AES and we would have AES.new. So how we'd actually create our AES, and then since our primitive, we're only gonna be doing ECB, and we're only gonna do single block ECB, but I don't think you can, there is no way to do that. We'll enforce that ourselves. This would be AES primitive mode. And I could pass in the value. I could just say 1, but I'm not, or use R variable, but I'm not entirely sure that it is 1, and then this just makes it more clear anyway what I'm doing. So if our key and our length of the key is correct, then we can create our little black box that's going to do the AES stuff for us, the actual encrypting. And if it's not, then we'll raise value error. Key must be bytes. Key must be bytes and 6, whatever. We don't probably really need this since it's just for our own use. It's not like we're making a package that we're gonna give to other people, but it's still good habit and practice to get into. And then we're gonna check our mode. Our mode has to be, right now we only have 2 modes, 1 and 2, so mode has to be one of those. Then we'll set our mode to mode, and if it's not, we'll raise a value error. Say invalid AES mode. Now, if I were actually like really trying to make it the same as PyCrypto, like I should go and see what their error messages are. But whatever. If the IV, we're going to check to make sure the IV has to be bytes, and it also has to be 16. Then we'll set the IV to IV. And if it's not, then we'll raise value error. IV has to be 16 bytes. And then, so kind of the way PyCrypto handles it. So when we call our new, we know that this needs to be bytes. The mode needs to be an int. And the IV, you know, I don't know how to do, because I want the IV to default to a random 16 values, because 16 bytes. Because if you don't give it an IV, then it just randomly creates one. So I'm not sure how you do assign a default and control a type. Like, I don't know then if you just do bytes. And I also don't know, we're returning, I think then you would do like, that's how you would check that what we're returning is a class that is AES. You know what, I'm actually, so there's no sense in like me making you guys watch me Google. So I'm gonna pause it and then I'll find out the answer to both of those and then come back. Okay, I'm back. So it seems to be like all things Python, it's needlessly complex because it changes constantly between versions, and I found a bunch of different answers. So I'm not entirely sure, but it looks like what you would do is, and again, none of this actually even matters because Python doesn't enforce this. This is just if you use a linter, which is a way to like, it's a helpful way to like make sure your code is doing what it's supposed to be doing. Like it, you know, it runs checks before it runs your code. And so if you were passing in something that wasn't bytes, it would, somewhere else in your code, it would warn you that that's going to happen. So even if you screw this up, your code should still work, but your linter might give you errors. So apparently it depends on your version, what version of Python you're using, what linter you're using. I don't know. There's so much really stupid things about Python when it's like such a, supposed to be such a like simple, easy language. And don't get me started on the Python 2 to Python 3 nonsense. Anyway, so I think you do it like this. You can just type it directly as what it is going to be, and you do it this way. But this, I was thinking about it, maybe I shouldn't be using, I think I did this in the first projects too. Like, I'm not actually sure what the best convention is. So my other option I'm trying to decide between is we'll set it to the default of none, and then in here we would say if IV, or again we could just say if not IV, if, because none also evaluates to false. So if not IV, that means if there's not an IV, then what we will do is IV equals urandom 16. And then now we would call our key mode IV. I'll just go ahead and leave it like that. I don't know. Yeah. So where were we? We created our init. I babbled about how we're going to use the primitive only to do our encrypting and decrypting. So let's go ahead and, so basically we're going to have two, air quotes, public functions. We're going to have an encrypt and we're going to have a decrypt. And in there, I'll just do this for now so I don't get, oops. And in there, we'll handle how we're going to encrypt or decrypt what mode we're in, because we'll have to do it differently if we're in ECB or CBC. But since I said like we were going to do the primitive, let's do let's call it encrypt single block. And we will take, we'll take a block. It's got to be bytes. And we're going to return bytes. Actually, let's just call it encrypt block. There's no block implies single. And since we're going to like make sure that we're only, because like our primitive, which is just the AES ECB mode, we could give it 20 blocks and it would return 20 blocks of ECB. So we could technically kind of make our lives easier by not having to deal with implementing separate ECB encryption and decryption functions, because we could just pass it to that. But since the kind of point of the exercise is to like build it up from the primitive, where we can't do anything but give our black box function a block and say, okay, return what AES would encrypt. We want to force it to be where you can only do a block. So you know what, screw that. I'm just actually going to say, no, I'll be good. This is what you'd want to do. So if anything ever gets passed to this that's bigger than the block size, it'll error out and won't run. And then what we'll do, these are the only places we'll actually call our encrypt and decrypt on from our primitive, which we instantiated right there. And then we'll do the same thing for decrypt the block. And it better be the size of the block. And if it is, we'll decrypt it. Or we'll return the decryption. Yeah. Okay, so now we want to handle how we're going to handle our encrypt and decrypt, because we want to be able to do both ECB and CBC. Well, let's go ahead and we'll do a little bit more error checking. That if it is not well, first, what is our, we're going to take plain text in bytes, bytes in, bytes out. Well, we need our self, which I also did not add here, because I always forget to do that. And we'll be returning bytes. And if it's not an instance of bytes, we will raise a map value error. Plain text must be in bytes. And then we also want to make sure that it is, since we won't be doing padding, that we make sure it is divisible by the block size. So if length of plain text modulo block size does not equal 0, again, we could just say if length if it's not 0, you know, I probably should. So here's one of the spots I struggle with, and then I get like super time wasty about, and I get all perfectionist with because I don't know. So like this to me seems more like concise and elegant, but it's also less clear. Quickly just reading it than that. But the main thing is I should be consistent everywhere. So if I'm going to do it this way, I need to do it that way in the other parts of my code, which I already haven't. So I'll just keep doing it this way. But the more I think about it, the more I feel like I should just do it the other way, because it's really easy, especially when you're new, which I don't know, consider myself, to like get caught up in trying to make everything as like concise and compact as possible. So like you'll see a lot of like people new to coding, like they'll have this function and it's a one-liner, but it's like completely incomprehensible one-liner. So you're just much better off having, 5 lines of code that's like readable and easy for anyone to understand than your super compact, only took up 1 line job. Anyway. So what are we doing? If it's not divisible by the block size, we'll say plain text multiple. I should look and see what the error is when you do it for an actual like PyCrypto, because it's like something like data is not aligned. What is it? From crypto. So we'll say new random. I don't care what the key is. Random 16 node ECB and then cipher crypt XOO. Data must be aligned to block boundary in ECB mode. What does it say in CBC mode? Data must be padded to 16-byte boundary in ECB mode. Interesting. Wonder why. I mean, you could do the same thing. It's just interesting to me they give you a different error message. Like if your data isn't aligned in ECB, it's because it must be padded. So why don't they just say data must be padded to block bound? I don't know, whatever. Didn't really help me any. So now we need to figure out how we're going to handle encryption and decryption, because we want to be able to do it differently depending on what mode. So I don't know if this will be the most compact way, but we'll check if it's mode 1, and if it is, we'll do something, and then we'll check if it's 2, and if it is, we'll do something different. So yeah, let's just have different functions for each kind of modes, encryption and decryption. So we'll have a, let's do ECB first. ECB encrypt. Well, we'll take blocks, or bytes, and return bytes. And then we'll have a ECB decrypt. And then we'll have a CBC encrypt. And we'll have a CBC decrypt. And then, so if it is mode 1, then that was ECB, that was ECB, so we will return however it is we're encrypting ECB. Oh, here's the other thing I always forget to do. Self.ECB encrypt. I didn't screw that up anywhere else. I don't think because I've called anything else yet. ECB encrypt R plain text. I guess I should make it plain text here as well. Yeah. Oh, you know, actually what I should do. That's why my brain was already thinking of it like that way. Let's, so we'll go ahead and in here, let's put that there now. We'll go ahead in here and carve it up into blocks before we pass it off. Now, really, it wouldn't matter. I mean, in all things programming, there's like a bazillion different ways to do the same thing, and there's often not a right or a wrong. But if we do it here, if we go ahead and carve it up into blocks before we pass it in, we're only carving it up into blocks here, where if we pass it in, we're going to write this same line of code to carve up blocks in each different mode we have, which would be okay if the method to carve up blocks were different depending on what mode we were in, but since it's always going to be the same, it just makes more sense. We'll write one line here instead of that same line twice, potentially more times depending on how many modes we have. So we're going to return ECB encrypt blocks, and then if it's mode 2, we'll return CBC encrypt our blocks. And then we will carve up the blocks. We can use list comprehension. So we'll say for I in range, we'll go from 0 to the length of the plain text, and we'll jump every time the size of the block. So we're going to iterate over a list. It's going to be 0, 16, 32, 48, all the way up until we get, so like, and then, well, I was going to give a different example, but we know the length of the text is always a block size, so it'll stop at there. So if we had a 64 byte plain text, it would be 0, 16, 32, 64, but it won't, so it's up to but not including this, which is fine because remember we start at 0, so if we went to 64, that would actually be the 65th byte of a message. So hopefully that makes sense why they don't ever include. It's not up to and including, because then it makes it easier to do. If it was including this, then you'd always have to write length plain text -1, because we don't want index 64, because index 64 is the 65th byte. No, we won't have a 65th byte. So for each of those, right, we're going to have, that's what we're going to, is in our iterator. So that's what we're going to be iterating over. then each entry in this list we want to be that portion of the plain text. And why is that not equals? So in that iteration, so like the first time we're going to slice up the plain text from 0 to 0 plus 16. And then the next time through, I is going to be 16. So we're going to slice. And remember, it doesn't include that. So it's 0 to 16. So it goes from 0 to 15. It gets the 15th index, which is the 16th byte or 16th entry. And then it'll be 16 to 32, so on and so forth. So that's how we're going to carve up that byte string into a list of byte strings. And then that's what we'll pass off to our different encrypt functions. So this should be good here. Now we'll basically do the same thing here. And I could be lazy and copy and paste. You know, just whack and then change everything where it says plain text to ciphertext. But I'm actually not going to do that because lately I've been finding, I think if you aggregated all the time that I saved in copy and pasting something and compared it to all the time that copy and pasting something introduced a bug in my code because I forgot to change something, the amount of time I wasted by copy and pasting is far greater than the amount of time I saved by copy and pasting. So I'm working on copy and pasting less. And then plus, here's what I like to tell myself, it gives me more practice typing, which is always a good thing. Because the better you are at typing, so see, I'm basically just reading off of that anyway. So I might as well be copying and pasting because I'm just going to blindly start typing plain text. So we're going to completely ignore that and try and write it the same. If the ciphertext is not an instance, if it ain't bytes, we want to throw a value error. So ciphertext must be bytes. And then we had another one that it has to be the size of a block. So if not ciphertext length modulo block size, which again I've decided isn't the best way to do it. It'd be more readable the other way, but I've come too far. We're going to throw a value error that the ciphertext must be a multiple of the block size. And then what do? We're going to carve that bad boy up into blocks. And then we're going to pass it off depending on what mode we did. So if self mode 1, then we're going to ECB, now we're decrypting. And if it's self 2, we are CBC decrypting. And that is it. So then our blocks, we said we had our iterator of for I in range 0 to the length of the ciphertext. And we're jumping block size each time. And then we'll carve that up by saying ciphertext I plus the block size. Let's see how good we did. Yay. Okay. So now we have how we're publicly being able to call encryption and decryption. We're just going to give it the byte of plaintext, which is exactly the same way we would do it for the air quotes real. Well, I guess I don't need to air quote that. That is the real AES. Ours would be the air quotes AES. So we're giving it bytes. It's returning bytes. We're doing some error checking. We're covering up into blocks. And then we're shipping those blocks off to how we're actually going to handle either ECB or CBC. We're doing the same thing for decryption. However we choose to handle that, the only place we actually get to use our little magic black box AES encryption is in these two functions here, where we only get to do a block at a time because that's how we're building it up from our primitive. So now, how do we do, ECB and, well, so ECB, we didn't have to do anything. There's nothing. We're going to encrypt a block and we're going to return it. So we can use list comprehension for this. And we can say for block in blocks. That's what we're going to iterate over, is each block in that list of blocks. We are just going to encrypt that block. So now we have a list of each block encrypted, but we don't want to return, right? Whenever you encrypt something, you don't get back a list, you get back a byte string. So we want to turn this into a byte string, and we can do that by just using the join function, which will just basically join everything in that list and separate it by whatever we put right here. And we're putting nothing there because we don't want anything in between them. Now here, we do the exact same thing, but this time we're decrypting instead of encrypting. So we're self decrypt block for block in blocks. Bam. So now we're going to CBC, which will be a little more complicated because we have to XOR some stuff, as we saw in this mode here. So when we encrypt, we have to XOR with the IV, and then each block, before we put it into our magic black box, we're XORing with the previous output. So let's actually get back to, okay, here we go. So let's go ahead then, and we'll set a previous block. And the first time through it will be our IV. And then here, I'll just go ahead and sort of write it out, and then if there's a more better way to do it, I can just change some stuff. So we're going to start out with encrypted blocks that is nothing. Then we're going to iterate over our blocks for block in blocks. And what we want to do, we said, was XOR with the previous block and then encrypt. So what we want to do is, I imported XOR, right? Yep. So we want to XOR our block with the previous block, and that is what we want to encrypt. And that is what our ciphertext block is. Maybe I should do ciphertext block, but whatever. And then what we're going to do is encrypted blocks. We'll add that to our encrypted blocks. So we're going to append the ciphertext. And then we'll set the previous block to the ciphertext. And then when we're done with that, we'll need to join all the blocks just like we did last time. Oops. But, so, I can't remember if I mentioned it or not. Since the IV is typically random, we need and you need this, right? You can't decrypt. You can't decrypt without knowing what IV you encrypted, because that's the first thing. So I guess actually that would only mess up. You could decrypt everything but the first block of text. Yeah, so without the IV, you can't get the first block of text back. So we need to include the IV with everything we encrypt. Otherwise, the person decrypting will not be able. They need the key and the IV if they want to recover the entire message. So we need to return the IV with it. And typically, a lot of the ways you see that done is it's just prepended to the encryption. So the first, excuse me, in this case, the first 16 bytes of anything we encrypt is going to be the IV, and we can just do that by prepending, because our IV is bytes. We can just prepend that to our. So we have our blocks. For each block, we're going to XOR and then encrypt. Then we put that in our encrypted blocks. We set the previous block, and when we're done, we prepend the IV to that. So that looks good. And then for decryption, it's going to be the same process, except, where is it? Except we're going to decrypt and then XOR whatever comes out of our magic function that does a yes. Whatever comes out of that, we're going to XOR with the previous block of ciphertext, which is our blocks, right? Because what we're decrypting is blocks that are all ciphertext. So we'll do the same thing. Previous block equals IV. And now we have decrypted blocks. And then for block in blocks, we want to decrypt. All right, we want to decrypt our block, and then we want to XOR that with the previous block. And that is what our plain text is. Then we decrypted. We decrypted blocks. We add that block of plain text to it. And now we set our previous block to be we'll set it to be block because, again, it's the previous ciphertext, and now we're working on the ciphertext, so that is our block. Previous blocks equals block. And then and then we can just return the join of decrypted blocks. And that should be good. It's a lot of code, and I wrote with terrible typing skills and no IDE, so the odds of this working first go are pretty much 0. But yeah, we got to do challenge 10. So basically we wrote all that so that now we have our own now we have an air quotes AES, and this is what we'll be using on all the challenges whenever they ask us to do AES, is the AES the AES that we built. So what they're asking us to do now is decrypt this file with the key yellow submarine with an IV of all zeros. So let's see what this file is. Okay, this file is just base 64. So I believe I was sticking that stuff in resources, challenge 10 text. Okay. We're good there. And then, so now we can, we want to, from utils, import AES. We're going to need to unpad their message, so import, we'll use our unpad. And then we have our if and our main. And then what we'll be doing then is our ciphertext, we're going to parse input of resources, change 10 text. And then we're going to create our cipher, which we call the same way as before. And then I could just stick all this in the function thing, but I'll just write it out so it's a little clearer. We're going to use the key yellow submarine, and our IV is going to be the 0 byte 16 times. So we give it the key. We're using CBC and our IV. So we set that up, and now we will decrypt it. Plain text equals cipher decrypt the ciphertext, and then we want to unpad. Remember, because padding will always be mandatory, so there'll always be padding. We want to unpad that, and then let's print that out. Print, and it's in bytes, so we'll decode it. Oh, we have to write our parse input function. So def parse input file name with open as with open file name as f. Let's see. We want to read in everything, and it's line broken up, so we want to replace line breaks with nothing. Oh, and then we'll need to base 64 decode that. So from base 64 import base64 decode. Import. And then we'll return B64 decode of the data. Okay, so, whoops. We should be go. Let's see how many bazillion errors we get of typos and stuff I made. So we have that saved. We have that saved. All right, the truth. Python 3, challenge 10. First error is cannot import AES primitive. Oh, maybe I. Oh, wow. So that whole time I was rambling about what I was doing here, there was just a glaring error. So we're importing AES, right? Because that's what it actually is, but we want to call it AES primitive. Wow, that's pretty bad. Because we want to rename it because we want to make it less confusing and also just for us, you know, in the code when we look at it. So that's why we renamed it AES primitive. And actually, I should be going through, now that I've written it, well, we'll make sure it works and everything, but I should then go through and comment everything so that when we come back, I mean, because this is a lot of lines, so we should be making some kind of comments explaining that, like, here is where our actual, you know, magic AES is coming from, and then these are our public functions that are the ones that you would call, and then these are all. But maybe I'll just do. No one really wants to watch me comment code in a YouTube video, so maybe before I upload it to the GitHub, I'll comment it. But so let's see what our next error is. So cipher AES primitive was AES. Oh, so that is line 11. So AES primitive, that's how we're calling it. So it's just AES primitive, that mode ECB. Bytes object is not callable. Line 41 in decrypt, we are, oh, okay. I dyslexiated that. If the length, oh man, if I had to copy and paste it, that wouldn't have happened. If length of ciphertext is not the block size. Yeah, I did it right up there. Name value is not defined. Line 42. Oh, value error. Oh man, another one. All right, maybe I got to go back to copy and pasting. Ciphertext. Okay, so what are we doing? We're decrypting the ciphertext. Is it not a multiple? It has to be a multiple block size. Line 42 in decrypt. Maybe I messed this function up. If length ciphertext, so if that's 0, oh yeah. So if that's 0, it's false. So yeah, if it's not 0, then do this. So how is our, maybe when I copy and paste it, I screwed something up. Because our ciphertext, we're parsing the input of challenge.10 text. We're replacing each new line and then decoding it. Let's, oops. Resources, challenge 10 text. Let's go back to copy it all. Okay. We're reading it, we're replacing new lines with nothing. With base 64 decoding it. And then we are decrypting it. And it's saying when we decrypt it, when we're decrypting it, we're getting that it is not a multiple of the block size. Or that it's not. Oh, wait a minute. This is wrong. So length. Oh yeah, so length. See, here's it. There's another good reason to not. So this is the way we want it, not this way. You know what? So I should have listened to my own advice, and we'll go back and check. If length, because we want this to be 0. If it's not 0, this will evaluate to true, and then that will happen. So let's just be, this is a good example of, let's be explicit so that we don't confuse ourselves. And then I'll go back. I think it was in the padding where I did that before. Yeah, if length padded modulo. Yeah, see, I don't have if not. So let's just go ahead and be explicit about it. And then we'll do that every time going forward, because clearly I get confused. Okay. Oops. Length. Oh. Line 44 in decrypt. So what I did here was there. Now I have one too many. Another one where copy and paste would have saved me. All right, we're typing we're being explicit and we're copy and pasting. Previous blocks reference plus 4 assignment 79. Oh, previous block, not previous blocks. See, all this is shit you would not have to deal with an ID and a linter and all that. Length blocks equals block size. Blocks is not defined. So in our decrypt and encrypt, unpad. Oh, I didn't give it to what we're unpadding it to. I always do that with padding. It's probably because I know AES is always 16 blocks, so it's like, why are we doing that? AES block size. All right, now you know what? Now I feel like it's going to work. All right, let's not pad this, and then we'll fix that in a minute. Now I'm just getting annoyed. We're gonna decrypt that. Oh, we did not decrypt it correctly. Yeesh. So we have somewhere in our logic, we have an error here. So our previous block is the IV. Decrypted blocks for block and blocks. We want to XOR the output of our decryption and the previous block. Decrypted blocks, we're pending. Why did I put pending text? No, that's right. We're appending the plain text because it's decrypted. And our previous block is block. All right, let's see if I get any of it right. So we can decode this. We say UTF-8, and then I believe we say, what is it? Let me look it up real quick. It's like escape error. I think it's replace. So what's this going to do? Yeah, what this will do is everywhere there's something that can't be printed, it'll make it a question mark. So this way I can at least see what. Yeah, so we're just getting nothing but garbage. Oh, we got the first block right. Okay, so I'm back and so we know we decrypted the first block correctly. Probably. So then it's got to be some error in here. Let's look at our map again. Unless we're appending it wrong in our parsing of our input. So when we're decrypting, we take the ciphertext, we decrypted that right. And then we're maybe messing up this previous block thing. So am I passing it to CBC decrypt? Let's check that first. So decrypt. Am I carving the blocks up right? Ciphertext 1 to block size for I in range. Oh, if it wasn't, we'd get an error because our blocks wouldn't be the right size, and when we passed it in there, it would be an error. So mode 2 is CBC decrypt, CBC. So mode 2, we're going to return CBC decrypt. We're calling decrypt, not encrypt. So previous block equals the IV. Decrypted blocks right now is nothing. So we're going to take each block of ciphertext. We're going to decrypt that block, and then we're going to XOR it with the previous block, and that is what our plain text is. And then to the decrypted blocks, we append that plain text. And our previous block is equal to blocks. How did it even, that should have thrown an error because I'm not, where am I getting previous blocks from? It should be like, it should have thrown an error. Previous blocks is, oh no, I guess I'm setting it there. So then it's setting some variable that never gets used. All right, well, that's a little, I always expect some errors, but I was a little disappointed in that one. I didn't do very well there. All right, there it comes out. So we've got it good now. Let's go ahead and let's not decode it. Let's make sure. And that's why our padding didn't work, was because we were decrypting. Oh, I don't want decode. We got gobbledygook out, so obviously gobbledygook's not going to end with proper padding because it's just random at that point. So we're 4 over. So now when we unpad it, unpad, and then now we'll decode it. So it'll look all nice and pretty. Oh. Every time I do that. Block. Oh, AES block size. AES block size. Yay! And it's just, I think that's the same one we had last time. One of the previous challenges. All right, well. Yeesh, hour and a half into it already. So now we're going, but we got most of the, I mean, again, what we would want to do really is we would do a lot of testing on this, give it various things to encrypt and decrypt and make sure, we did all that correctly, but we'll find out as we go along whether or not that's working. So now we can go to challenge 11. Okay, so now we're gonna write kind of like an oracle. Although I'm kind of annoyed by that. I don't. To me, this wouldn't be an oracle because an oracle kind of like gives you, I guess this does give you information. I was gonna say an oracle kind of gives you information. Like you don't. It's kind of a way to like. So a way to think of an oracle is like think of like some, super higher intelligent alien being or something, and they have the ability to answer questions. Like you could say, like if there was there's going to be, I think we even do it in one of this set. There's going to be, I'm sure there'll be something with a padding oracle, and basically you can give it ciphertext, and you don't get anything back. It won't decrypt it, or it won't tell you what the decryption is or anything. But it'll basically, you can think of it as an oracle. You're consulting a higher power, and you can say, here's some ciphertext. Is that properly, or here's some ciphertext. When it's decrypted, does this have proper padding? And just having that oracle, like you cannot know what what the encryption, like you're not doing any of the decryption, you're not handling any of that, you don't know anything about the ciphertext. You don't need to know the key to AES, but just knowing whether or not what you're feeding it is properly padded is you can actually recover plain text messages. So that's kind of like what an oracle is. So I guess technically this would be an oracle in the sense that, I don't know, you're giving it something and it's either giving you back. I still don't like the term for this for oracle. Anyway, we're going to create something that's going to encrypt a message, and it's either going to encrypt it, it's going to prepend and append stuff to it, and then it is either going to return ECB or CBC, and we have to tell which it is. I feel like that would be the oracle, but whatever. So let's do that. So challenge 11, and we have if main. Oh, well, we're going to need our, so from utils dot, we're going to have to pad. So we'll import pad and unpad. And we're going to have to encrypt stuff. So we'll import our shiny new AES. And yeah, I think that's it. We'll find out. So let me kind of think how I want to do this here. Oops, ear itches. Because I know in the next challenge they're going to want us to kind of reuse this, if I remember right. Copy oracle. It's going to change it. Okay, well, so here's what I'm thinking. If we just sort of, maybe this would be a good opportunity to explain something too. This, if we just sort of wrote it like kind of how they say, so encryption oracle, and then what is it? It takes, oh, I won't even worry about that. It's going to take bytes, and it's going to return bytes. And then it does stuff in here. Actually, we can go ahead and write that out. What does it do? It we will need from random import, because we need random. I think it said 5 to 10, and then make those bytes random. So from OS import, could just use one of the random ones, but random. So I don't know if I've ever talked about it. Basically, if you get random, randoms, random, if you were to ask random for a series of bytes, they're not cryptographically secure bytes. Basically the way the random number generator works isn't good enough for security for cryptography. And one way to get secure bytes randomly is to use from OS import random. Because then what happens is in the background of the OS, I'm not sure how it works exactly, but basically it's collecting entropy, depending on what keystrokes you're typing and what stuff is being run on the processor or whatever, is how it kind of generates random. So it's it's a more random, and that's random enough to be cryptographically secure. There's also, if you can use, there should be a random one in the PyCryptodome. I forget what it is because I always just use random, but it'd be crypto utils random bytes or something like that. But so basically, whenever we could just use a random one here because we're just prepending in text and stuff. But so whenever you're just generating random keys and stuff or IVs, use a cryptographically secure random. And then I always just use urandom because it's always available in Python, and It's just kind of the one that I always use because that's what I learned. So what they say, 5 to 10 bytes. 5 to 10 bytes randomly in the front and 5 to 10 bytes randomly in the back. So, why did I name it bytes? We'll just call it data because it's, and then so we're going to get rand int. So rand int 5 to 10 will return a random integer between 5 and 10 inclusive. So 5 and 10 will be in there. And then we want that many random bytes. And then we're going to prepend that to data, and then we'll do the same thing on the back end. And that is what our plain text is going to be. And then half the time we want it to do, so then we would have if rand int 0, 1. So it's going to either be 0 or 1. So if it's a 0, this will be false. And it'll just do what we were about to say in the next. So if it's a 1, it will we'll make it do AES. So then we would say cipher equals AES new. Oh, so it said a random, the same key each time. So we'll say key equals. So it's always under the same key. And then, so this would be 1, so it would be AES mode CBC. And if, so in AES, I think I mentioned this, even if it was CBC, if you don't give it an IV, it just makes a random one for you. And we're not actually going to be decrypting anything. So like, we don't care. Basically, we're just trying to tell if, and then we would return cipher encrypt our plain text. Yeah. And then if it was not a 1, then we do the same thing, but now it's ECB mode. And then we would return cipher. Oh, I guess actually, here's what I could do. So we don't need to, we can do it this way. So the cipher is going to create depending on which method this is, and then we have to pad. So we have to remember, because our AES does not and should not worry about padding. That's a separate thing. So we have to pad our plain text to the AES block size. And then we would have our detection function, our CBC, ECB, CBC detector. And then we'll give it, it would take in ciphertext, and that is bytes, and it will output a string on whether it's ECB or ECB. And then basically the way, so like we already know, right, that if it's ECB, if we, since we control this data here, we control the input, like we don't know how many bytes are in front and how many bytes are in the back, but we know that if we give it enough bytes that are the same, we'll generate the same, like the way we tell something is ECB is if it has duplicated blocks. And the way we need to get it to duplicated blocks is to give it, is to make sure that no matter what random numbers are on the front or the back, that we've given it, we've ensured there's at least 2 blocks of data that have the same byte. So like the easiest way to do that would just be, we're going to give it the string A 48 times. So that's 3 blocks of A. So no matter how you put something in the front or in the back, doesn't matter how many, what they are, somewhere in there, there is going to be at least 2 blocks of all A's, and those will always, if it's ECB, decrypt to the same thing. So we're going to give that to our encryption oracle, and then we'll I forget which one did we write where I had duplicated blocks. So we would say it was challenge 8. We'll just reuse that function. Contains dupe blocks. Oops, where am I? So, and then we would say return ECB if contains dupe blocks, ciphertext, otherwise return CBC. Yeah, and then in our main function, we would just run this a whole bunch. Basically, we would we're giving it bytes. So we actually would just run ECB detector a whole bunch of times. What it gives back is the output because it's generating the string and it's calling the encryption oracle. So basically, what I'm going to do here is because I don't like this because we're just doing functions and it doesn't make a lot of sense to me. It's so like. First off, I mean, I know part of it is hard, right? Because we're supposed to think of this as this here is some black box that we don't know, what's going on inside. But it's just we give it something, it encrypts it and gives us back, and then we have to tell whether or not it's CBC or ECB. And so it's kind of hard to we have to write that, but then pretend we don't know what's going on about it. But just kind of as a way to sort of make that explicit that it's like some separate thing. Like we could think of it as like some website or some service that we're interacting with. Like I'm going to go ahead and make this a class. And then when we initialize that class, then we can generate that key, so it'll always be the same. And we want 16 bytes. And then basically it just has an encrypt. That's going to take data, bytes, and return bytes. And then it'll do all that stuff in there. It would do all of, I believe, we don't need the key. Yeah. Oops. Except now it would be self.key and self.key. So now it's more separate, right? At least to me in my head, it thinks it's more of an external thing. Now we have to create that class. We're more interacting with something. But what's going to happen here is now in our detector, like we also want to think of our detector, right? It's just sort of this tool. And we give it this tool. We're going to use this tool to check whether or not some ciphertext that we got was, or whether or not this actually, so we're going to use this tool to detect whether or not this encryption service we're interacting with, if it's giving us back ECB or CBC decryption. And so right now, what I want to get to kind of talk about, I guess, is these are very much like dependent on each other. Well, so this is dependent on this encryption oracle, right? Like we're going to have to instantiate it in here. And then like, so it's dependent on that. So if we ever change the encryption oracle, like this tool no longer works. So it's kind of like they're coupled together, right? This is dependent on this. And so kind of a way, there's one way to decouple it. Like how, so when we originally had a function, they were very coupled. Like they're both in the same class, and it's like dependent on each other. And it's then super hard to reuse that code later on because like now we have these classes and or functions, and like it's just hard to like pull them out and stick them somewhere else. So we made this a class. This will now be easier to use later on because we can just take this code. We don't even have to take this code anywhere. We could just import this module and grab this here. But this our CBC ECB tool is still very much dependent on this. And so one way to kind of like decouple that even further is to abstract it one layer more out. So like in another language, we would use what's called an interface. But Python doesn't really do interfaces that well. Like, I don't know, it gets really complicated. But what we're going to, here, let me go ahead and write it, and then maybe I can explain it better. Encryption Oracle interface. And let me go ahead and, so def, it's going to have an encrypt. It's going to take bytes and return bytes because that's what we always do. And we're not going to do anything in it. So one thing here is I'm using, what is this called? So camel case is where the first one's not uppercased, and then every new word after that is uppercased. And I think this is duck casing. I mean, there's duck typing, but I don't know. This one we're doing it where the first, it's always capitalized, the first letter, even the very first one. And this is sort of like the same way that the underscore symbolizes like it's sort of a private inner method. This casing simplifies that it's an interface. And the way an interface works is a lot of times we're better off if we program to an interface. Like if we're going to try and decouple this, right? We're going to say we want this tool to work whether or not we give it this exact encryption oracle. Maybe we want to change this. Maybe we want to give it different ones. So if we can somehow make it where this just takes something that is guaranteed. So what we're going to do is we're going to give it something that we're going to tell it, okay, we don't know what we're going to give you. You don't know what you're going to have, but we're guaranteeing you that it's going to implement this interface. And what this interface says is that there'll always be an encrypt function, and you're going to give it bytes, and you're going to return it bytes. So now our tool doesn't have to depend specifically on this exact encryption oracle. We could give it anything we wanted. Doesn't matter what the class's name, doesn't matter anything, so long as it implemented this interface, we could still make this tool work correctly. Now, it gets kind of in Python because they don't really deal with interfaces well. Like this is actually, what is it called? It starts with an I. This is going to bug me. It's not like there. I'm going to look it up. Python interface. It is called a, no, I'm not going to unAdd block or create an account to read your crappy blog article. Why is that not? Maybe it'll pop into my head later on. Anyway, there's different kinds of interfaces, and in Python, this is a implicit interface. That's not the right word. Anyway, it kind of defeats the whole purpose of an interface, because like in where I'm used to like C#, you have to, your class has to implement every method in the interface. And in Python, you can still ignore it. There's ways to make it then where you can check to make sure, but then it gets like really complicated, and we're not going to do all that. I don't even know how to do that, really. We're not going to do that because it just doesn't make sense to do that. But I want to get across this idea of writing code that's not so tightly coupled, and so that it's like easier to reuse later on, and it's just a little more abstract and a little cleaner. So like with our thing now, we would also, so like it's a little bit different because this is just a function, but like if we were thinking about this as a class, like our tool is a class, instead of instantiating, one way to do it, so like we're creating this specific class in our tool. So right now it's tightly coupled, because if we ever change this or do away with it or change it, like this tool is no longer going to work. But if we do it to an interface, and this isn't how you would do it in Python, but you could make it create an object or a class that implemented that interface, and it would be a little less coupled, because now we can give it different ones. And if we don't have this exact one, we could still make it work. But a better way to do it is what's called like dependency injection. And there's different ways you can do it. But what we're going to do is we're going to say, okay, we'll give you the tool, and you're not going to know what class it is. It's not going to matter, but we're telling you, actually, I think I can just do according to my new research, because I thought you had to do type encryption Oracle interface. But I think we can just say, if that thing I just read a little bit ago was correct, we're going to tell you that Oracle, so actually, no, I remember now, because we're not actually going to give it, because again, this is the way Python works, we're not actually going to give it an encryption Oracle interface. That'd be if we were giving it that. But we're going to give it something that implements that. And the way they kind of do it in Python with this type of interface that I can't remember what it's called, is we're actually just going to make it the subclass. So our encryption Oracle is going to be a subclass of encryption Oracle interface. And so that's how this is telling, or for the linter checking, it's saying we're going to give you encryption Oracle, and this will be an encryption Oracle interface or any subclass of, which is what this is going to be. So now we don't actually have to instantiate and create it in here. We're giving it. We've injected what it's going to need. We've injected what this tool is going to need. So now we can just say, okay, we don't know anything about how we're going to get this. So let me write it out. Oracle. We don't know anything about whatever function this is calling, but we've told our tool that we've guaranteed that it's going to implement encrypt. So we can be assured that we can call the encrypt function and give it bytes, and it will get bytes back. And then so we could change this. We could call it something completely different. As long as it's implementing this interface, this code here won't break. And that's a much better way to do it. Now we could easily more separate these. We can plug different things in. It's just much less tightly coupled. I'm trying to think. Yeah, whatever. I don't want to get too. I'm trying to think. I don't want to have to because I think in the next challenge we are going to need to check for dupe blocks again, and I just didn't want to have to put this method everywhere. And so right now this like if we were going to separate this tool into its own class, we need to make sure to put this because it relies on this function. But if contains, oh yeah, we had to tell it a block size. And then so just in our main. So now in our main function, we can create our oracle equals encryption oracle. And then for just run it a bunch for, and again, you use the underscore when you don't actually need to use the word. We want to iterate something 100 times, but we don't need to keep track of it. So then we would just say ECB CBC detector, and the only thing we have to do, we have to give it, we have to inject into it the oracle, and then this now will spit out whether or not it's ECB or CBC. But we need a way to actually test this. So let's add in some code to test what it's actually doing. So we'll tell it, we're going to give it a list, and then each time it does one, it will append. This is what, CBC. And then now that we're back to copy and pasting, this is ECB. So now there'll be, in this encryption oracle, there'll be a function or a parameter of list. So it'll keep the history of everything. So that way we can actually check it whether or not we're doing it correctly. So we'll create our own list called detections, and then in here we'll append to detections whatever that says, whatever our detector says. And then what we'll do is we will print, maybe I should just do it 10 times, because then I can do our cheesy testing and say, did we get it correct? Let's check our detections. We'll check our detections versus Oracle's history. And then again, if we were actually like, this is just so we could test it, because like the reality is, I mean, maybe you'd want to have a history, I don't know, but like we're not actually supposed to be able to like know what's going on inside of here and stuff. Or I mean, that's sort of how we're supposed to think about it. We have to detect what's going on without knowing how it's actually implemented, which is why they gave us the random, right? Because we're not supposed to know what's going on internally. And then well, let's just go ahead and do that. I'm sure I got some errors we'll have to fix. Yeah, let's just see where we're at. You random. Oh, another error in our AES-Py. You random. Line 87. I just fixed that. You random is not defined. Did I not import it? No, I did not. From OS import you random. Oh, duplex takes 2? I thought I had to give it 2. I was looking at it when I decided I needed 2. Oh, no, it does just take 1. Why do I want I to 32? don't remember what we were doing. We must have been doing it on hex. I bet we were doing it on hex strings. So here, let's just change that, and we'll say, now we'll give it a block size. And then we know it's just like the other function we've written. I'm trying to think if there's a way I could just one liner. I should be able to just one liner that. Blocks equals whatever. Oh, we got it true. So let's try it for 100 times now. And then maybe I should have just printed out 1 so we can at least see. Here, I'll do it 10 again, and then I'll print actual, and then we'll give it our Oracle history, and then on the new line we'll give it expect. I want to line them up. Expect, and that was our detections. Detections. Destroy. Oh, I needed a new line. Now I'm just getting nitpicky and wasting y'all's time. Oops. Oops. There we go. See, now we can easily. I was like worried for a second. Oh no, we're only doing CBC. So we had a bunch of CBCs, ECB, ECB. So those line up. And then let's do 100 of them. Let's really make sure we get it right. And we still got them all right. Okay, so now I don't remember why I was doing 32. Then we must have been doing, maybe it was hex it gave us, or did it say it was 32 byte blocks? Whoops. Whatever. So now we can move on to challenge 12. And now, yeah, now we start getting into where it's more fun. So, yeah. So we see in this one, we're going to take the Oracle from last one, but we're going to change it. And we are basically, they give us some secret encoded plain text that we don't know what it is. And we're going to append it to whatever we input into this function. So like, here's an example. We're AES 128 ECB encrypting our string concatenated with what the unknown string is, and it's all done under a random key. And what's going to happen is, without knowing the key and just being able to make repeated calls to this function, we're actually going to be able to recover what all of this is. And it kind of goes into how you do this here. But I'm going to go ahead and, I mean, they do a pretty good job explaining it, but I'll go ahead and just show it a little more, or at least like verbalize it so maybe it makes it clear or whatever. So basically we have, let's just pretend our secret is just 1 block long, and we'll say it is, well, here's our little block of secret. And there's not actually 16 in there, but whatever. Let's, each one of these is a byte, and we don't know what they are, But let's say in actuality it is, I think, a secret message is 16 bytes if I remember right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, so that would be exactly a block. Now we'll ignore the fact that there'd be padding after this, but it won't matter. Actually, let me write it a little. A, secret. I'm not spacing it out well. Message. All right. So here is what it actually is. Now we don't know. Whatever. This doesn't. But we can control whatever we put in front of it. So like if we just put like hello, which is 5 bytes, then this would get appended to a secret message, and then when it goes through the encryption, it would be hello, 5 bytes, and then it would take the first 11 bytes of this, so a space secret, how many is 11? 16, 15, 14, 13, 12, 11, down to E, maybe. I might be off by 1, but whatever, it doesn't matter. And then that would be the first block that would get encrypted with ECB. Now we know that ECB, every time you, if it's under the same key, every time you encrypt a block, you get that exact same, like that plain text will always be that encrypt to the same ciphertext. So let's say, for example, we gave it a block of 16 A's. And then after that, the next block is going to be this secret message, which we don't know what it is. But so we know, we'll be able to tell afterwards what a full block of 16 A's looks like, because a full block of 16 A's under that key will always produce the same ciphertext. So what if instead of giving it 16 A's, we give it 15 A's? Then it's going to be, the secret message is going to be appended to the end of that. So at the end of that, we'll get the A from a secret message. Actually, let's do it this way. We don't know what it is, but I probably shouldn't have picked a secret message since it's an A. The first one's pretty easy. But we don't know what it is, but the first byte of whatever the secret message is will be in this block. So if we send the encryption oracle 15 A's, what we'll get back is the first block is whatever the encryption is of 15 A's plus whatever the first byte is of the secret message. Well, then what we can do is send 15 A's and then every single possibility for a byte value. So we'll send it 15 A's and then the byte 0, 0. We'll send it 15 A's and the byte 0, 1. We'll do that for every single possible, there's 256 byte values, 0 to 255. We'll send all of them. Then all we have to do is compare which one of the 256 we sent matches the one we got back when we did 15 A's and what the secret byte was. The two that match will be, or the one that matches to this one will be whatever the secret byte value was, which in this case we'll figure out it's actually an A. So then we'll just do the same thing. Next time we'll send it, now we know the first one is A. The first secret byte is A. Excuse me. So we'll send it 14 A's. Now we're going to send 14 instead of 15. And then we'll send the first byte of what we now know the secret message is, which was also an A. And then what we'll actually get is the 14 bytes we're sending, and then the first 2 bytes of the secret message will be in this block. We know the first byte, so now the unknown is this one. So we'll do the same thing, although we won't actually have to this time, right? Because we already know what all the A's is, so we could just look. But we'll send all possible encryption values, and then we'll find out the match. So then we'll find out it's a space. So now we know the first 2 bytes are we know it's A and a space. So now then next thing we would send 13 bytes of the secret message. Or sorry, 13 bytes of A's. So here's what we are sending. Then we know the first byte will be A, the second byte will be a space, and then our unknown byte will be that. So then what we'll do after that, we'll get whatever that is, that equals some value, we'll just call it X. Then we'll send we'll send the block of all A's plus an A and a space, and then every single, I'm at the end of the thing, so I'm getting sloppy. Every single possible byte value, right? And we just keep doing that over and over until eventually we recover the whole message. Now, in the case of the actual message, it's going to be more than one block. So we'll do a couple things. First, so they also want us doing, I don't know why they want us doing this, but they want us to find out the block size, to discover the block size, which is annoying because AES is 16 bytes. It's always the same block size. And then we'll detect that the function is ECB. And then we can start doing, like they explain basically what I probably didn't explain any better. So let's just go ahead and set that over there. Kind of jump jump into this. So if we do challenge 12 now, so we'll be reusing our oracle, and we'll be reusing our detector. This still, I'm going to actually, hold on, I'm going to change this. We don't actually need that function because I don't know, this is just bugging me. So we're going to we'll just do it all inside of there. So blocks will be, we're carving up that. And then what we'll do is if and that shouldn't change anything, but now we get rid of this, so it's just a little less hassle. Let's make sure it still runs it okay. Block size is not, oh. So we need to say get it right. Okay, so let me just change that back to 10. So if we ever do run it again, we don't get that whole long output. Okay, so we're going to reuse our detector and our oracle, and we're going to input this, the encryption oracle interface, because we'll do like how we did here. We'll code this new oracle we're using to the same interface where we know we'll have a decrypt function, and then when we're doing our recovering stuff, we can do it that way with like the dependency injection. So we're going to we'll need pad and unpad. We'll need AES. That string they gave us is base 64 encoded, so we'll need, sorry, it's B64 decode. And then from challenge 11. We'll import our encryption Oracle interface and our, what do we call it? Was it ECB or CB? ECB CBC detector. ECB CBC detector. Okay. And then we won't need a history. Well, we won't need any of this now. We're not randomly doing stuff. And we will keep the key because we want to do it under one key. We won't know what it is because it's just 16 random bytes. And then the plain text is going to be the secret message, base 64 decoded. So here, let's do secret equals okay, so that's the secret, and then we'll base 64 decode that. And then our plain text, or I wonder if I should make it, yeah, let's actually put it in, because it's the same for every single instance of this Oracle. So we'll actually put it up here. Let's do self.secret equals, then I'll just do it all in one go. Equals base 64 decode. Actually, we encode bytes, but we don't need to decode bytes. So actually, it doesn't need to be a byte string. I think it still works if it is, but. And then now, our plain text will be whatever the data is, whatever message we're giving it that we control, plus secret. And then what we're going to return is, I need to create the cipher. Since it's always going to be CBC, we can just create it up here. Equals AES new our key, and then we need node CBC. We don't need an IV because it'll just give it a random one. We don't care what it is. Yeah, because we're just encrypting, so we don't care what the IV is. As long as it's this. Oh, now I'm confusing myself. Oops. No, go back to that. Yeah, so what pen? It's the IV. Yeah, so it has to be the same IV each time, which that's fine. If that's how this will set up, that cipher will always have the same IV. It's just some random one we don't know. Then we have our secret. And then what we'll return the plain text, which is our input plus the secret bytes. Be padded. And we'll return that encryption. That should all be all we need for our Oracle. Now, the first thing they want us to do is recover the block size, which will be pretty easy, right? So let's say the block, we're 4 over of some block. So it's like 4 bytes and then 12 bytes of padding. So if we give it an input of just an A, maybe I should draw it. Just to make it explicit. So if whatever the last block is let's just say world. So then there'll be 11 bytes of padding of the byte 11. If we then, and there's, whatever is in front of this, right? There's other blocks. This is just the last block. And then when we send our A, we're going to send, our input is going to be the A. It's then going to push everything over. So this last byte, or this last block, will now be, if it was like this part over here was hello world or something, like now it would be the space from hello world, and then now it would be world. I don't know why I make my blocks so short. And then now it would be 10 bytes of padding of the byte 10. But us sending it, what I'm trying to show is us sending it one character didn't actually change the output size, because we're just bumping out all that padding. When we send it 2 A's, the final block now, instead of having, it went from 12 to 11, now there'll be, oh, that wouldn't be 10. That wouldn't be 11. 11 is B, and 12, or 10 is A, because these should be in hex. Anyway, now there'll be 9 and then 8 and so on. So we just keep feeding it A's every time, one more A, until eventually we bump all the padding off, and then now it has to create, like when that last block finally ends with, hello world. And now since padding is mandatory, now it will create a whole block of 16 bytes of the byte 16. So at that point, it'll jump. So we've been feeding the A's, and say what we get back is 160 bytes. Right, so there's 10 blocks. Now all of a sudden, we're going to jump up to 176 bytes. So then once it jumps, then we can just subtract them, and then we'll know, okay, each block is 16 bytes. So we'll just write a function called get block size. And then we'll inject in, because we'll need to be interfacing with the encryption oracle. So we'll inject in our encryption oracle. And what we will return is an integer, which will be the size of the blocks. Oops, I'll go ahead and down here do my okay, so we'll have our first time we'll send it an empty one, and then let's check and see what the base length is. Let's go baseline, and that will be the length of Oracle encrypt, because we know it has an encrypt because we're programming it to that interface. We'll encrypt test. So that's whatever the base length is. That would be however many blocks the actual, right, we're pending nothing to secret message, or prepending nothing to secret message. So our secret, what we're going to get back is how many blocks secret would actually take. And then we want to have a new length. And we'll just start that out by setting it to the base length. And then what we can do is say, while new length equals base length, we're going to increment test by, we're going to add another A, and then our new length is now going to be whatever it is when we encrypt that. We're encrypting our test. And then so this will just keep iterating until at some point it pushes everything off, and then we get back a new block, and then now the new length will be a block bigger, so we can just return the new length, which will be bigger minus whatever the base length was. So in our main, we are going to create our oracle equals yes. Oh, wait, no. Our oracle is just a encryption oracle. And then we're going to get block size. It's kind of annoying because we don't, well, we'll just, here, actually, we can just test this one first. So let's say block size equals get block size oracle, and then we'll print it out. And then we can run that. Oh, base 54 decode. Oh, okay, yeah, because we're setting the key from OS import to random. We're using it here to set the key to some random value, so we need to import it. Oh, there's again, I always do that. I always forget myself. Okay, so we see the block size is 16, which we already knew. So then what we do now we can go ahead and start working on how we're going to recover those blocks. To do that, let's find out how long the secret is, size of the secret, and we get that by just encrypting nothing. So that would be the length of our oracle when it encrypts nothing. And then we'll do a function called recover secret, and we'll have to be interacting with our oracle, so we'll give it to the function. And then we'll want to know, the size of the secret. That is an integer. And what we will return is the secret. Now, since it wants us to detect that it's using ECB, what we'll actually do to make sure is we'll just run an assert. Like, we can only use this tool if the, what do we call it, ECB CBC detector on the oracle equals ECB. So this recover secret function is only going to work when the oracle that we gave it is encrypting in ECB. And then let me think. So the way we're going to do it, so I showed you how to do it a block at a time, but we're going to do the full, like, what we need to do if we want to recover more than just a single block, and then this way we don't have to iterate over. I think it'll, in my head, it'll work in my head it works a little better. If we go ahead and whatever the full size of the secret is, we're going to give it that many A's off the start. So if this is 10 blocks, it's 10 blocks. We'll just, for the sake of argument, say this is 10 blocks. And then they're carved up somehow, blah, blah, blah. There's 10 of them, pretend. And then, so the first time through, we will send it all A's short of 1. See, the long block line is a carved up block, and then the little line is just the last space in the last block. So we'll give it all A's up to that point. And then we'll do like how we did before, where we will encrypt all A's. So it'll be all 10 blocks of A's up to last byte, and then we iterate over everyone, and then we look for a match. And then if we do it this way from the start, we shrink back the whole way until the very, very end. We're just feeding it a single A. Then we've got 9 blocks of the secret message we already know. Secret we know. And we're down to that last block of we know all this stuff here, and we're just looking for that last unknown. I don't know why that looks like an R. It's supposed to be a question mark. That last unknown. So if we start from the size of the secret, we can work back the whole way, and I think that'll make it just a little easier coding wise, because we're not going to get a block and then have to shift the block we're looking at. So to start out, let's call it, I think is input I think input's a keyword. Let's call it feed, because this is what we're feeding it. So we're going to feed it as many A's as the secret size. So if it's 160 bytes, we've got 160 bytes of A's. And then here is what we recovered of the secret, which right now is nothing. And then we will iterate over however long the secret is. And then what we'll do is each time through, we need to shorten our feed by a character, right? Because we'll have recovered a character of recovered a character of the secret. So we need to now we need to make our feed one shorter. So we'll say our plain text, which isn't actually really plain text. Maybe I should just call it data. I don't know. Whatever. We'll say is feed to the negative I, right? We want it, so if we found 1, we want to go up to but not include the last one. And then our ciphertext will be what we get when we encrypt it. And that ciphertext will come back with our feed is the encryption of the concatenation of our feed plus the secret message. And what we're trying to match then is everything up to the size of the secret. Yeah. So we're trying to match if the secret is 16 or is 10 blocks, then we want to look at the first 10 blocks. So we'll end at, so if this was 160 bytes was how long the secret is, we want to take everything up, we want to take the first 160 bytes. So we want the ciphertext to stop at the 160th index, which would leave 160 bytes before it. And then, so now we know what we want to match, right? What this will be is all A's plus what we know of the secret, which right now is nothing, and then plus there's less a single byte, and we're trying to now find that byte out. So we're going to iterate over every possible byte. So our test is going to be the plain text, which is what we've got our feed of, however many A's we actually want to give it, plus what we've actually recovered of the secret, and then our test byte, which when we loop, right now this is an integer, so we need to convert it to a byte because we have to feed our encryption oracle bytes. And then we can test if what we get when we encrypt test the first secret size bytes worth is equal to what we're trying to match it to, then we know that that was the byte value that what we were looking for. That's the one that was in that little window that we were trying to find out. So then we can just add that to what we've recovered, and we can break out of this loop now. And then so now we've recovered one. Now it'll go back up, and we'll feed it one less A because we've got one more recovered. So now everything gets shifted over. And then when we're done, we'll return the recovered. Now the first time through, really I guess what I should say is for I in range from 1 to secret size, because feed, so whenever you take, like let's say we have a string of A's and there's 20 of them. If you do A, we slice it off to the -0, you're just going to get an empty string. So it's going to basically, it's not going to find a match the first time because we didn't actually feed it anything. So it'll just go through, not find anything, and then it'll go on 1. So really it would be the same as if I went like that. But I don't know, to me that just makes my brain itch less because somehow it's more concise. And then I think that's good. We've got the block size, which we don't actually really need. So now we just want to say that our secret is what we get when we run recover secret, and we pass in the oracle and the secret size. And that should be the bytes of the message. So then we could print the secret. All right, now let's find out how many mistakes I made. Line 32. Okay, so it is not detecting that we're doing an ECB. Oh, yeah. Our detection oracle works. I mean, that's actually why I did this. Two reasons. I wanted to see if you guys were paying attention, and wanted to make sure our oracle was working. That's the story I'm going to go with. Ooh, it's working. Oh, sweet. Okay, it worked. So the secret message was, I mean, it would have to be that. There's no way that we randomly found something that did. You know, monkey slapping the typewriter, and we came up with a random one that worked. But just to be sure, from actually, let me just import base 64, and then we can do base Cool. There. Okay, so now we can actually move on to challenge 13, which is ECB cut and paste. Okay, so basically what we're going to be doing here is we're going to write a function that takes kind of like a parameter list and turns it into an object. And then we're going to write a function that takes an email address and gives us that object, but encoded as those parameters. Okay, so basically what we're trying to do here is we can think of it as like, again, since we're going to have to write it because that's how we have to do it, but basically what we're going to write basically is think of it as like some service on the internet you would interact with where you're going to give it, like you're registering for an account or something, right? So you give it your email, and then on the back end it's going to create, you know, a user ID for you, what role your user is, and your email, and then okay, so it's going to be a weird service, but basically imagine there's some service where you sign up and register an account, or and it, you know, in the back end creates all this stuff and encrypts it, and then for whatever reason it's going to give you that encryption back. It's going to say, oh, here, we created your account, here is the encrypted information from your account. And then what we're also going to do is say this same service for also for some reason, not only do they just decide to encrypt encrypting your stuff is fine, but then giving you back that encryption, they're also going to have a way for you to say, hey, here's some encryption. This is who I am, decrypt it, and I'm going to be that user now. So say you would register by giving them an email address. They create all this stuff and then give you an encryption. But then you log in with this encryption. Actually, yeah, so let's say this was the only way this would make sense, is say there's some website and they couldn't afford a back end or storage. They want to they don't want to save anything. So you can sign up for an account, you give it an email, and it creates the data, encrypts that, and gives it back to you. And that's what you use to log in, because it's kind of like, you can think of it like if you're familiar with like a JSON web token, kind of think of it like that, where except it's encrypted. So you're going to give them that encryption string, and that's how they're going to authenticate you. The service will decrypt it and then decrypt it, and it'll parse it and be like, oh, okay, this is, you know, user whose email is foobar, their user ID 10, and their role is user. And what we're going to do is, if there was such a service, we are going to try and trick it into having it think that we are an admin. We're actually going to authenticate as an admin, because we're going to use the fact that they will encrypt what we give them and they give us back that encryption, and the fact that it's ECB, which we know has vulnerabilities in the fact that every plain text produces the same ciphertext under the same key, and we're going to trick it and authenticate as an admin, and that's why they're also not allowing us to encode meta characters and an equals, because like what would happen if one way some stuff, not really anymore, but in the past you can, well, I mean, you can probably still find it out there somewhere. But like if you were to actually say your email was foobar.com @role=admin, and then it'll encrypt all that for you, and then when it decrypts it, it looks, if it's just looking for, oh, what's their role, it'll see role=admin. So that's kind of a way to bypass it that way. So we're actually, they're thinking about security, so they made their service so that you can't do something like that. So, but we're going to show how if they're using ECB, we can still exploit it. So let's go ahead. I'll code up the service first, and then I'll show you how we're going to do what we do and why it works. So if we do, we're on 13. So we're gonna need our AES. We'll have to pad things, so we'll need padding input, pad. All right, so let's just call it, and like we could do these as functions, but I'm gonna go ahead and like make it as just, again, do like I've been doing. I'm gonna make it a class, and sort of that just like, you can think of it, it helps me at least think of it as a more separate entity. It's like some abstract thing over here or over there that we're interacting with. I mean, we had to code it, but like this is basically like you would, I mean, you'll see this exact same kind of challenge in like CTF, crypto CTFs, and even some web CTF stuffs, where you're basically interacting with this service, and this is what you're going to do to like hack into it. But they don't provide us that. We have to code it for ourselves. But just to, I ramble too much, just to make it seem more like it's this separate sort of entity thing. And let's just go ahead and call it, it's some service. And what this service does, what did they say they want, is profile for. So we need, it's kind of confusing the way they do this. So it should take something like that, create an object. So we'll have some function called profile for, and it'll produce that stuff, but encodes it as whatever. So we will have, well, they're going to have to, we're going to give it something, and then we're going to have to, they will encrypt it. So we'll call the function that we can interact with encrypt profile for. And it's going to take an email address, because that's just what we give it, which is a string, and it will return bytes. Now, in reality, I should probably make it so it like returns a string as well, because if it was, say, like basically you're never like transmitting bytes. Like if it were going to return the encryption as bytes, that's why things are base 64 encoded or hex encoded, because you run into problems doing that. So really, if it was some service, they would return like base 64 encoding of the encryption, or a hex, that really they would probably do a hex encoding encryption. But just for ease, I'm just going to go ahead and keep it bytes, because that'll just make it easier for us to interact with. That way we don't have to decode and encode and all that stuff, which won't change at all like the ability of you to do this challenge or anything like that. But I'm just mentioning it because like if you were doing this in a CTF or something, you'd be interacting with an actual like web server or like a netcat server or something, and they would be giving you, they'd probably just be giving you hex back. I don't know. I'm just rambling again. And then what it's going to, so we actually will need an init. So And we'll create our cipher here. And it will be some random key that we don't know, but it'll always be the same key. And it will be ECB. And I'll do ECB this time because I don't need to trick you guys. That's all we need there. And then we'll also have a function for decrypt profile. Decrypt profile. And this is sort of like how you would log in. And again, we would really be giving it a string because that's how you'd be interacting with it, but just for ease. Yeah, I'll go ahead and make it, I think you do it this way. I'll make it a dictionary because what we're getting back when we authenticate, just for this challenge, like I'll just have it return whatever object it decrypted your information as, so that way we can see. Our goal is to make it what it sees as role user. So I'll just have it give it back to us so we can look at it, and that's how we'll know, ha, we hacked them. And then, so when we encrypt a profile, we're giving them a string, and they said they wanted us to turn that into an object. Yeah, so we'll go ahead and make a, what they call it, profile for. So we'll have a function that turns that string into and it should produce encoded. Okay, so basically we can skip this step when we make it, because basically they want us to take this, it'll produce this, but we're going to encode it as this to encrypt it, and we don't want them to be able to put in ands or equals. Just trying to think. Yeah, so then we'll do a separate function that takes something like this and actually produces that object. I forgot. So we'll have a function called, what did we say we needed one? That was profile for, and it's going to take that address and it's going to return bytes. Yeah, that'll be the actual profile. Yeah, just trying to think here. And then we'll want one that is, we'll call it param parser, and that will take params that are bytes. Well, actually, maybe I shouldn't do bytes because no, it'll always be I think we could just leave it as strings, because when we're going to encrypt, we can return bytes, but instead of having to convert everywhere along the way, yeah, let's just do it that way. We'll keep it as strings because we're just parsing parameters here and we're creating a profile. There's no reason we have to do that in bytes. Yeah. And then we only need to turn it into bytes when we actually encrypt it. So this will also return a string. And param parser is how we create the actual object. So here we'll return a dictionary. And then we won't get too crazy. Like this wouldn't be the way you'd want to do it. But we'll just split it on, we'll split it on ands, and then we'll split on equals. So like, we're just going to go ahead and assume we're not going to put any error correction or making sure that we've gotten a properly formatted string, because then we're just adding complexity. We don't, I mean, the point of the challenge is to figure out how this works, not actually create the service. So we will just, we'll split for param in params, split on the and sign. Then we will take that param and we'll split it on the equal sign. And then we will turn all of that. So then what we'll have is, so this for param and param split, it takes that string and splits it on the ampersand or and sign, and it'll be, this returns, this is an iterable, like this is a list of all those objects. So it'll be a list with email equals foobar.com, and then the next item is UID equals 10, and the next item is role equals user. And then it is going to split each one of those on the equal sign. So then we'll have a email foobar UID 10. So basically we're going to get two things on each one. So we get that will be our key values. So then we can just turn that into a dictionary, and that is what we will return. Yeah, and then the profile for one is the one where instead of quoting them out, like how you would handle characters in a string that you get like through the web or something, if like you don't want them to be able to use those, you just escape them out or replace them. But since we're not actually going to handle, it's kind of funny, right? I'm like saying like we're not going to build this with error correction and stuff because we're handling complexity that we don't need. But then I'm trying to figure out how we make it so that if somebody gives us the things we don't want, even though no one's going to do that because we're not trying to actually build something that's going to be in use. So I'm just going to do if and is in address or equals and in address or equals in address. Not on my watch. Address cannot contain and or equals. Yeah. And then we'll do return. We'll return the F string, and what do we say? They want an email equals address, because we're only taking, we only take the email address, and then it was UID equals 10 and role equals user. You know what? Let's go ahead and make it so that, I mean, this is kind of phony because everyone is the same UID. So let's actually, we'll make that increment. We'll keep track of what the next UID should be. And then here we can do, we're going to have to increment that. So we cannot return that. We'll say that, this is the profile. And then after we do that, we need to increment what the next UID will be. And then we can return our profile. So keeping track of the UID, every time we encrypt a profile, we're going to get that profile, which then here's where we check to make sure they can't use the forbidden characters. And then we turn it into that string they wanted us to have them as. That's what we're going to encrypt. We'll increment the next, so the next person will have a new UID, and we'll return that profile. So then what we want to do here is return the encryption of that profile. So we'll return the encryption of, well, we have to pad it, and it is a string right now, so we need to make it bytes, and everything gets padded to the AES block size. So now we just need to decrypt something. So let's see, we are going to have to decrypt. And what we're decrypting is the profile. And then we kept it in bytes because we're just trying to make it a little easier because we're cheaters that way. We're going to have to unpad that, which means we need to know the block size. And we'll have to decode that because it is bytes. So those are our params. And then what we want to return, because I said we want the dictionary so we can check, we can see kind of how they would be, how they're evaluating it. Like, so in reality, it would be like whatever they decrypt. This would really be like the, I don't know, process login, or, you know, that's how you would read the cookie and then get the, you know, information or whatever. But since we don't actually have a service, we're just going to return what they're going to see it as. So then we need to parse those parameters, and that's how we'll get our dictionary. So we'll say return param parse params. So that should be our service. I feel like that should work. I'm sure I've got typos and some errors, and God only knows what else. So now, how we're actually going to do this. Let me bring my little notebook thingy over here. So, okay, here we go. So, what we're doing, they tell us what we should do. They don't actually tell us. Okay, I was just seeing if they like kind of explained how to do it like they did in the last one. So we know, what we know is that with ECB, right, and this is why it's going to be called, why it's called ECB cut and paste. If we get a block of plain text it'll always output that same block of ciphertext. So if we look at our message, email equals, and then we have a little bit we can control. We control this right here. We control. And then, it was, and UID equals 10. And I cannot draw ampersands. That's the music note symbol. And role equals user. And we want, so basically what I'm trying to, what we're going to try and do here is we're going to create more than one account, and we want to make it so that we can basically cut out blocks. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So like this right here is 13 bytes. Make sure I counted that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. So this is 13 bytes. And we know so we want our final message. We want it to be email equals something. We don't care what it is. And then we want it to be and UID equals 10 and role equals admin. So basically what we're going to do is we're going to cut and paste things together from different ones to get something in this format. And so we know that in that format we definitely want, we're going to need a and UID equals 10. Well, we're incrementing it, but that won't matter. And role equals, so we know we're going to need this section. So this is 13 bytes. So somehow we need to get a block of this plus 3. Now we don't have any control on this end, but directly in front of that, we have control right over here. So we know email addresses end in .com, right? So if what we controlled here was we put in whatever we wanted, and then we got the last 3 to be com, if we lined this up right so that this broke on a block right there, then this com and UID 10 equals role and equals would be a block of stuff that we know we're going to want, right? Because our final, our email address ends in com. We want some email address, but we want, so actually, yeah, let me maybe, an email address ends in com. We want something with an at. We want some stuff here. We don't care, some stuff here, and it's going to have email equals in front of it. I should have left myself more room. So what I'm saying is basically we need to figure out how to make this a block. And we do that by making sure there's exactly 16 bytes in front of it. Well, we can't control this, so we know that is 1, 2, 3, 4, 5, 6 bytes. Oops. No. Anyway, this here is 6 bytes. So if we give it something that is 12 bytes, so if we give it something that is 12 bytes of whatever, and then .com, actually just com, so we want 11 bytes of something. We want 11 bytes and then .com. What we'll get then is the second block of whatever we get back is going to be this com and blah, blah, blah. So we'll have that part of our final. And then all we'll have to do is somehow make something that says admin. But so if we have 11 bytes to come up with an email address that we're going to use to log in. So if we do Did I count the, hold on, let me make sure. 1, 2, 3, 4, 5, 6. So that's 6 bytes plus R3 is 9 plus the period is 10. Yeah, so if we just did oh yeah, so that's why I'm confused. It won't be 11 bytes. So we know we need .com. And we know email equals takes up 6. .com is 4, so that's 10. So we have 6 bytes of user-controlled input. I mean, we control this too, but we need 6 bytes in here, and we need an AND. So let's say ABC at, I don't know, me.com. So if we user control input, send it that, we will get we can use the first 2 blocks, because what we'll get back is email equals abc at me.com. That should be 16 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15. Whoa. Apparently I am bad at counting. 6, 7, 8, 9, 10, 11, 12, 13. Oh, that's 16. EMEA, all right. I guess I shouldn't worry. No one's watching this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, that's exactly 16 bytes. And then this at UI, oh, that's only 13. Oh, so we don't, okay. It doesn't matter what we put here, because we're just going to keep, oh, man, I wish I could just redo this, because I effed it all up. We want, okay, so let me start over. Maybe I'll figure out how to edit this. I don't know. This is a block that we want. So we need 16 bytes in front of this. So email equals is 6. We need to put 10 bytes of gibberish in there. So if we did, and one of them will be a dot. So here we go. Here's 10. So if we do, the user supplied input we're going to give it is blah at blah.com. If we do that, then we'll have an email equals blah at blah.com. This right here will be a block. 1, 2, 3, 4, 5. Wait, E-M-A-I-L. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that will be a block. This com and UID equals 10 and role equals will be a block. So then we've already got the first 2 blocks. Equals right here is 2 blocks. So this was a block. This here is a block. And this here is a block. And we want to keep both those, right? Because if we make those the first 2 of what we're going to authenticate with, we're already good. We've got an email address, .com, and a UID equals UID, and a role equals. So now we just somehow need to come up with a block that ends in admin. And if we want it to end in that, right, that would be the last block, we know we'll have padding. So admin is 2, 4, 5. So we want 11 bytes of padding of the byte value 11, which would be XOB. right? Because that's 10 in hex. So we want 11 bytes of that. So then we could create another we'll create another user, because right, we can supply input for something else, and we'll make it somehow in our input that we get a block that is just that. So we could say our address, we know we need gobbledygook, like an email equals, and then we know from before we need 10 bytes. So we could just say our email address is going to be the byte value, or A 10 times. I don't know why I put 2, 3, 4, 5, 6, 7, 8, 9, 10. This right here is a block. Then we'll give it that, and then we don't care what we put after it. So we're going to put that there. That's a block. And then we're still in our user control. So then we could say at we.com. Like, it doesn't matter. So our email address for some account we're going to create, the email address is going to be 10A's admin, the byte value 11 times at we.com. That's what we're going to give it. And then we can go back in when we get that, and we will take whatever the second block of encryption we get back is, because the first block is going to be email equals all these A's. The second block will be this, and then we don't give a crap after that. And then we're going to take that second block, and we'll stick it on the end of what we already did here. So we're cutting off the last block we got when we registered blah at blah.com, and instead we'll change it with this block. And then when we feed that to the decryption, it should see email equals blah at blah.com. The UID is 10, and our role equals admin. When it unpads that, then it get rid of all that, and it'll parse it, and it'll think we are the admin. So now all we got to do is just write that up. There was something I wanted to say while I was rambling. I thought of something, but now it has escaped me. Oh well. So now we just need to code that. So if okay, so we have to create our oracle. That's what we'll be injecting into some service. Wait, we don't actually. Oh yeah, so yeah, our oracle is actually how we're going to interact with the service. In my head, I was already thinking like it was actually a separate service. And then so we're going to encrypt a profile for, we'll call it blah, equals oracle.encrypt profile for, and what do we say? We want to make it blah, where's my ampersand at blah.com. And then what we get back from that, well, let's go ahead and here, we'll do it. Let's go ahead and blah. So what we get back will be ciphertext. Let's actually print, just to show that it works, what we get when we decrypt that. Oops. So blah, we're going to create a profile for blah.com. This will be the blah will contain the encryption of that. And then when we, air quotes, log into this service, we're going to give it blah, it's going to decrypt it, and then we should get an object back, and that would like show us what user ID and stuff we are, how the service actually sees us. Oh, oops. Oh, sweet, it worked first try. So email blah@blah.com, UUID is 10, and our role is user. And this should be let me just double check that the length of that should be 48. Oh, length of 48. Blah should be 48 long. Okay. So what we actually want then, so yeah, let me go ahead and we'll do it like this. It'll look cool when we, at the end. Okay, so we are going to, now we're going to, we'll get some garbage account we don't care about. Garbage equals Oracle encrypt profile 4. What did I say we needed? We needed an A 10 times. Or was it 11 times? Email was 6. So we needed 10 A's. And then we needed oh, here's where we could run into a problem. Because I think we're going to get lucky and it won't matter, but I'll explain it in a second. We needed an A 10 times plus admin. And then we needed, just to make it a little more readable, let's actually just do it. 2, 3, 4, 5, 6, 7, 8, 9, 10. Admin plus byte value x0b. And we need 11 of those because I don't want to write that out. Since we're actually taking a string, right? Here's again where we get into problems with bytes. We're going to get lucky here because say instead we needed padding, like, I don't know. Actually, they're all ASCII characters, so I think we'd still be okay. But basically, I was worried that we need to convert bytes to a string, and if so, what we're needing to convert isn't a printable character or is some gobbledygook that, like, say, I don't remember what is. So OP is 11. What is 11? Oh, is that going to screw it up? No, because it's going to encode. So it takes the profile 4, it sticks that in there, and then it encodes it. So that'll, okay, we'll be fine. Basically, this is why nothing you interact with, you just don't send raw bytes. Well, I mean, everything's raw bytes, but because you run into problems. I'm like, say this was a new line, like, because byte value 10 is a new line. Oops. Yeah. So then say I had to send 11 new lines, and then depending on how the backend that we don't know the code, how it's working, when it goes to parse the profile and make stuff, maybe all those new lines screw it all up. So you could run into problems with something like that, especially if you're using it by, actually it wouldn't matter because even if we sent it a string, well, if we send it a string of all new lines, maybe it interprets the string. So maybe that's what I'm trying to get at, is you can run into problems with this. That's why everything's often like encoded in hex or base64, or I mean, that's why base64 encoding exists, because you want to be able to send ASCII characters over the internet, because byte values raw bytes kind of mess stuff up. That's what I'm trying to basically get at. But the way this works, we're going to be okay. So just hopefully you're watching this at least double speed, so I didn't waste as much of your time. And then we want to call it, we want this to be encoded. I'm trying to think of like a non-ugly way to do this. Crypt profile 4 garbage dot decode. That would need to be bytes. So it's going to be that byte string, and then we want to decode it into garbage account. And then we don't want, so what we get back, remember I showed was, what we're going to get back is email equals at and all that stuff. We don't want the first block, we want the second block, because the second block of what we get back is going to contain this block that we want. So then what we could do is say our pwned login is going to be the first two blocks of blah plus the second block of garbage account. And then so actually just I wanted to print that just to show what this is actually. Let's go ahead and print what happens when we not blah garbage account. And then now we will print what we get when we log in with our pwned account. And this one, what we should get back is that we're user ID 10 and that we are role equals admin. This one here, this we should, just so that it won't screw up the parser. What we say, we're just gonna make it, we can make it whatever we wanted. At haha.com. All right, I think this should work. Okay, so we see here we created email, blah blah at blah. Our UID was 10. Our role was a user. Then we created the second one, which was this really stupid looking email. It had the UID of 11, right? Because we incremented our UID, so every person that gets done. And this account was also user. And then we combined, we copied and pasted out because we're using ECB. We created this account out of that, which now we could log in, because now when it decrypts those to look and go get the information for the session, it'll go, okay, the email is blah.com, UID is 10, and they are an admin. And all we did was use our own user supplied input, create 2 accounts, and then from that we gained admin access. So hopefully, I feel like I just went on forever, but hopefully that makes sense. So now we can move on to challenge 14. Okay, so it looks like we're doing the same thing as 12, except now there is a random count of random bytes prepended to every plain text. A random count of random bytes. And prepend this string. Okay, so it's the same one every time. Now you're doing random prefix, what we control, and the secret that we want to get, all under a random key. And our goal is to... So basically, so it's going to be a lot like challenge 12, except for the simple fact that now we have this stuff in front, and we don't know how much stuff there is. Well, we don't know what it is either, but we don't care. Basically, we just need to figure out how much stuff there is in front of it. So like before when we did challenge, let me bring my thing up. Where did I put it? Before when we did challenge 12, erase all this stuff. We were basically starting from the beginning. So like when we were comparing, we, like if here were our blocks, at some point, well, we knew how big the secret was, and then we were using all A's at the start. And then comparing each time we encrypted and decrypted, we were comparing that link there from the very first all the way up until, and that was as long as the secret was. And then we slowly worked our way back. We got rid of A's. We brought down with stuff we know. Now we can't do that because we've got some amount of stuff in front that we don't know how much it is. And then we have what we control, where we're going to stick in all our A's. And then we have our secret. But if we knew how much stuff there was in front, then we can do the exact same algorithm we did before, except where before we compared from well, we could do it 2 ways. Yeah, okay, so if we knew exactly how much stuff was in front, then basically we can do the exact same thing, except now because it's ECB and everything decrypts the same, if we know how much stuff is up front, we can make this prefix stuff that we don't know. If we know how much it is, then we can pad whatever we want. So we'll say P's just to make it clear. We're going to pad enough, we'll stick enough P's in to make it the full length of a block, so that every single time, whatever all these blocks in front, we don't know what any of this stuff is, but we don't care. It'll always decrypt to the same thing. And then we can compare that. We'll do just like we did before. We'll stick A's in. And then our secret that we're trying to figure out. So now instead of comparing from the start, where we got to start putting our input up until the length of the secret, now we'll be comparing the start, which a bunch of crap we don't know, some crap we control to fill that up to the same block size, so it's the same every time. And then we can use our same algorithm of as many A's as the secret message is long we want to recover, and then we'll just use the exact same algorithm. So our goal is we need to find out how much prefix there is, so that we know how much to stick into here so that we start on an even block. Now the way we're going to do that is we know that, so we'll have the prefix that we don't know what it is. We have, there's concatenation sign, our input, and then we have the secret. The first time, if we just encrypt, we don't give it any of our user input, what we're going to get back is the prefix concatenated with the secret encrypted, right? We don't know how many blocks either one is. But if we are user controlled, so we could stick in just a single A. And now what we get back, however, basically, I think I gotta say this, whatever block in the plain text that A ended up being in is the very first block we're going to see a change. Say the prefix is 38 bytes long. That means there's 2 blocks of prefix, and then there is a block with 6 prefix bytes in it. Then it's going to be our A, and then the secret. Well, the only thing that changed between these two, the first 32 bytes are going to be the same because it's still the same prefix. It's just now. So we've got, let's say, 2 blocks of prefix. Then we've got this third block now has some prefix and our A, and then started the secret, and then however many more blocks there are. Over here we had 2 blocks of prefix, and then the third block had a little bit of prefix and then the secret. And then, oops. Good. And then, you know, however many blocks after that, whatever. So the third block is the one that changed. So we can find out by, we'll encrypt with nothing. We won't give it anything extra. Then we'll encrypt with an A. And whichever is the first block that changes, so this block and this block are the same. This block and this block will be the same. It's the whatever block changes is the block where the prefix is going to end in. And then what we can do is, so we don't know where at in that block. Like, so we have our block. We know the prefix ends in this block. We don't know where it ends, but we know that we can just keep filling it up with A's. And every time we encrypt that, it'll be different, except at some point, we'll have filled it up completely with A's. And then when we go on to the next block, now we're adding our input into the next block. Now when we get the encryption back, suddenly that block that before is going to now be the same decryption, if that makes sense. So like at some point, we're going to fill this block full of A's. This here was prefix stuff. We don't know what, we don't know how many. At some point, if we keep adding A's, we'll fill this block, and then no matter how many A's we add after that, forevermore, the decryption of this block will always be the same because now we've moved on. So what we're going to do then is when we'll find the block where the prefix ends, and we'll start putting A's, and we'll keep putting A's in, and we'll checking this block in the decryption, and then at the first point this block no longer changes value, it stays the same, then we know we filled it up with A's, and since we know how many A's we've made, we can simply count how many there are, and then we'll know how much prefix there is, right? So if there's like what did I say earlier, 38, so then we'll keep filling stuff up until it gets to 48. So it'll take 10 A's to fill that block, and then we'll know, okay, 48 minus 10 is 38, so there's 38 bytes of prefix. So hopefully that makes sense, and if not, hopefully as we go along with the coding it will. So the first thing we're going to do is reuse our encryption oracle. We're going to add pad and unpad AES. We need the code. We're not going to check for ECBE. Did I say EBC? Okay, no. I always mix up. I know it's electronic code book ECB, but I always end up writing it EBC. So we will need the interface because our encryption oracle, we're coding it to that interface. So we have the same key every time. We're creating the cipher. But this time now we have a secret, but we also have some prefix. And we have a random bytes of, we'll need random import. We'll use randint again. We want a random number of bytes. Oh, we want random bytes, and we want a random number of them. We'll go from 1, so there'll always at least be a byte of prefix, and then, I don't know, we'll go up to 42. And then our secret is the same. We'll just have amnesia and pretend we don't know it. And then now when we have our plain text, we'll also be adding the prefix to it. So it'll be prefix, our user controlled input, and then the secret that we're trying to figure out. And now we're going to do almost the same thing we did in challenge 12. We'll need an oracle. And then we are going to recover prefixed secret. And we'll give it the oracle. And then we'll simply print that out. Secret decode. Because we'll get it back in bytes. Hey, we're done. So now we just need to write the, this time we'll have the recover prefix secret, which will take an oracle that is some form of encryption oracle interface, and we're going to return bytes. And then we need to know the prefix size. Prefix size. And we'll have some function that does that. Get prefix size. We'll need to interact with the oracle for that. And then we'll have our prefix fill. Those prefix fill. We'll fill that up with, we'll use P's instead of A's. Not that it doesn't matter in the slightest, but just sounds better in my brain. P for prefix. And we want as many of those as, basically we want to take the prefix size and keep adding P's. We want as many, how many P's will it take to get to the next multiple of 30, or next multiple of 16? There's got to be like an elegant way to do it. Probably something simple that I'm brain farting on. Well, let's take, if we take the prefix size divided by 16. So 2 slashes in Python is floor division. So like normally if you were to do 34 divided by 16, you get a float. But if you do 34 double slash divided by 16, you get an integer back, floor division, so 2. So that, but we want the next highest, because this will give us one lower. So we could just, Oh no, that's how many P's we want. So this should be a lot simpler than I'm thinking in my head. Let's get the ceiling division. So we're going to ceiling divide it. Now you can call math.ceiling, but the kind of fancier way, in my opinion, that works better, and although it's going to look confusing until you know what it is. Basically, we're upside down floor dividing. So we're floor dividing, but since it's a negative, it's going to go to the next lowest number. So like 34 divided by 16 is 2. Well, it's 2.125, right? And you floor divide that, so you go down to the next integer 2. So if we did 34, well, okay, so 34 divided by negative 16, why do I keep doing 24? You're going to get negative 2.125. So if you floor divide that, you go down to the next integer, so you're going to get negative 3. And then since we don't want a negative, we flip that back over to a positive. So this is just a way to ceiling divide without having to call anything, any outsides. So that will be how many blocks of actual prefix there is with it filled. And so we want to subtract from that the prefix size. All right. So let's say there was 38 bytes of prefix. That would be, there'll be 3 full blocks of prefix, which would be 48. So this here will go to 48. And then we subtract prefix size, which was 38. So 48 minus 38 means that we need to put in 10 P's to fill up all those blocks, or to fill up that last block. And then, like before, we'll get secret size. And that is just going to be the length when we give it, when we encrypt the prefix fill, right? We give it enough P's, we fill it full of P's. And then from that, we're going to subtract what the total, like here when we got 48, that's what we want to subtract from it. So I could write the ceiling divisor again, but instead I'm just going to put I think it'll help with clarity, prefix size plus the length of the prefix fill. Although maybe I should just go ahead and do the same thing here. Or I could just do this in a line, like say, I don't know, give that a variable name and then could reference it in both spots. I don't know, I'm probably just doing that thing where I stress about making it perfect. And then let's look at what we did in 12. So now we can basically just repeat this algorithm, except we'll have to add prefix, those P's in front of that. And then we won't be comparing to the secret size. We'll have to have a different one. Let's go ahead and write it like this, and then we'll go back and look. That way we can check that our brain is working right. So we'll call it the same. We'll call it feed. And then this time we're going to do the prefix fill plus as many A's as the secret size is. And then now, before I think we had But we didn't use anything. We just used secret size to compare. But we're going to need a new length because we can't just use the length of feed because that forgets about all those blocks in front of it. We also could instead also just do slicing, right? Like we could just get the index of where our A's start. And then we could always just compare that. And that would just be, again, this number. So maybe we should make a variable for that. Because then that would be where we start comparing, and then we would end comparing at that number plus the secret size. I'm trying to think which. I don't know. Let's do it this way. Our compare length, and that will be the prefix size plus the length of our feed. Because the length of our feed is the size of the secret and then how long our prefix fill is. So those two added together will be. And then when we compare, when we do our string slicing, instead of like start, end, we'll just have a end. So maybe it'll take a little less room. I don't know. It's one of those things where there's like a bazillion different ways to do it. And I don't feel like I'm good enough to know what I'm sure I would, like, if I watch like someone who, just has been coding forever and they're super good at it. And like, I would look at the way they did it and be like, that's like so elegant. I wish I would have thought of that. But that's just like a product of experience and time, and just keep churning out crap, and eventually you'll get there. At least that's what I hope. That's what everyone says. And then we'll do it just like before. Whatever covered, and then for I in range, how long the secret is. I think we used secret length last time, didn't we? That actually sounds better. I should do, I want to look now. No, I did use secret size. I just wanted to make it like consistent across both. So then before we had our plain text equaled the feed up to whatever I we are, which is how many we recovered. The ciphertext is going to equal the encryption of the plain text. And then we're going to match ciphertext, that many of them, the length we're comparing it to, and then we go through all our bytes for be in range. So 0 to 255. We want the test is going to be the plain text plus the recovered plus the bytes of B. And then if that encrypted is the same as what we're looking to match, then we know our recovered is that byte. And we break out of that. And where out of that we can return recovered. Okay, so let's see where So really the only thing that should be different now is instead of whenever we compare stuff, we're comparing to this compare length. Otherwise, the two functions should pretty much be identical. So we had our extra line in there. And now when we compare, we're comparing not to secret size, we're comparing to that length. We're encrypting the test, we're comparing it to the length, it's to match. Bytes breaked, okay, yeah, we look good. And we know that worked because we decrypted it once, and we're not worrying about the detector anymore because it didn't tell us to. And so now, although I guess before, so we passed in secret size. And now we went and got it ourselves. Actually, probably should have just made it, get it in here. Whatever. So now we just need to find I believe the only thing we need to do is recover prefix secret, is get this prefix size. So we will create a get prefix size, and it will take an oracle, and it's going to return an integer. Let's see, how did I say we did this? We want to find out which block we stick got the A. Let me think. So to do that, we're going to say, how do we want to do this? If we use prefix size. So there's kind of like two steps to it, right? I'm thinking in my head that we want to find out what block it starts in. And then we want to find out how many we have to fill it up with, how many A's we have to fill it up with. So I don't want to do all that in one function because you kind of basically want your functions to do, ideally you want them to do just one thing. So I'll write another function that is going to actually get start index final prefix block. So this will tell us, this will return the index that the wherever the final block of prefix is in. So if the final prefix is 38 bytes long, this would return us the integer 32 because that's where we want to start looking, because we don't care, we know everything before that is going to be the same. So we want to start our comparing, we want to compare bytes 32 to 48 when we start adding A's. So this will also interact with the oracle. And it's going to return an int. Oops. So the way we do that is we want to have one where no A's are added. So we'll say no add equals oracle encrypt, just the plain text, and then we'll have one where we added. And then we want to compare those, and the index where if we lined both strings up and just started looking at them, the index where there's the first difference will be the start index of whatever block that A got stuck in. So we can actually, let's do it this way, and then we can do something new too. So let's say, so like how I said, we're going to line them up and compare them. So that we're going to zip no add and add. And I think I talked about it in the last one, but zip is like basically, you can just think of them like it's zippering them together. And so if you have two strings, like here, I'll actually do it. So let's say A equals A, B, C, D, E. So that's, and then B equals 1, 2, 3, 4, 5. So when you zip these two together, you're going to get, actually here, I'll make one longer just to even show what happens, because it only goes up to the ones you can actually compare. So like if we do zip AB, what's going to happen then is we're going to get so is that like a generator or is an object for item in last evaluated function? Let's print it out. I think we're just going to get a bunch of tuples, and I think I can do it this way. Yeah. So yeah, it gets A1, B2. So it lines them up and it only goes to the end. So we're gonna zip them up, but we want to know, right? This doesn't give you indexes, and we want to know what index the change is going to have to start at. So we're actually going to enumerate, and this one is pretty one I haven't showed before, I'm pretty sure. So another way, so like if we had a string that was, I'll just make it gobbledygook. Now normally if we were just to say for character in A, print A, it's just going to print out all those, right? Oh wait. Yeah, why didn't it do? Oh, because I said print A, not C. For C in A, print C. It'll print out, it iterates over and prints out each one. But if we said for index I and character in enumerate A, now what's going to happen is print, we'll use the F print so we can show it. Here's the value of what I is going to be, and here is the value of what C is going to be. And so I will be the index and C will be the character. So it should print out 0K, 1J, 2L, yada, yada, yada. So now we're going to get that zip. So now instead of like how this was just a character, we're actually getting a tuple. So it'll be like how we'll get, so when we do this, we'll get the index of that. So it'll be 0, and then the tuple with A1, 1 with the tuple B2. And we're going to be comparing the tuple and the one, because they'll line up, right? They'll be the same all the way up until that block, and then the decryption was different. So now the tuples won't have the same character in it. So we want to enumerate up to that. And what we're going to do is we're going to say for I, and then A, B, N. So we're getting two items out of this, the index and then that tuple. And then we want to add if A does not equal B, then put that index down. And so now, so like if we did this as a list, right? It would be a list of all the indexes where the two characters from each list are not the same. But if we, instead of, because we only want the one, right? We just care about where this first happens. So we could get this list and then take the 0th item in that, the first one, which would be the index of that. But we can also just make this a generator function. And a generator function basically, or a generator, I don't know if it's actually a generator function, but, or they just call it a generator. But basically is, it doesn't create the entire list all at once. It just sort of like gives you the next one. So, which is what you want to use for a lot of stuff when you have like, or like if you were going to make a list, but it would be like, I don't know, 1,000,000 items long. You can use a generator instead and then get the next item as you need it. So the way you get the next item out of a generator is by saying next. So next is a function that takes a generator, and with only that input, it gives you the next one. But if, so like, let's say we compared two strings and they were, that's it, they were lined up perfectly. There were no A always equaled B. So there would be no next item in here, right? It'd be an empty list if we were going to make a list. And so as a generator, it can't get you the next item because there's nothing in it. So what you do for that is you can specify what you want like it to return if there's nothing, that the generator is empty, there is no next. And we want it to return 0 because if there is nothing in the generator, then that, well, actually it wouldn't matter. We're never ever going to get nothing because there's no way that they're all going to line up. I guess if we had it where, yeah, if A does not equal B. Actually, no. Yeah, because if A doesn't equal B, it's going to give you the first one. So I was just trying to think like if somehow it worked where it didn't return anything, we want it to return 0 because that would be, we would start at 0. But that's what we would do if instead we had it for A equals B, and then somehow we wanted to go at the end of that. I don't know. Basically, we don't need the 0. But I'll just put it there anyway because then that, I don't know, it just helps show that there you can get, like we could put, I'll put whatever here. You can put anything here and it'll return that if there's nothing in there. I'll just leave it at 0. And then we can just return that. So it's going to return the first I. It's going to grab the first index from that generator where A didn't equal B. And then now we can do prefix size. So that's going to give us the first index. And so we could say like start equals get start index of the final prefix block. And then we can we want to get, we'll say our previous, and because we're going to compare previous and next encryptions and find where they finally stop or where they start being the same. So previous encryption of, we'll call this one our previous encryption, oracle.encrypt, where we give it nothing. But we're going to be looking at the start and start plus. Now, if I were going to be better, I'd probably say AES.block size, but since AES is always 16 bytes, I'm just going to put this magic number here, which is, right, like if someone's looking over your code and then they don't know that AES block sizes are always 16, this is much more confusing than if I had AES block size, because then it's like, oh, okay, it's explicitly obvious what I'm doing here. I'm comparing a block, where if it's just start plus some number, like, what the F is that number? I don't know. Like same thing here. I should use block size. But since I'm making the text big and I don't know, I don't want too long lines. AES dot block size is just way too many characters, and I can't be asked to deal with that. So we're going to do that. And then we'll have our, we've been calling it feed. And then we're going to, while we're busy doing new things, let's go ahead and do some walrus operator. So we want to have a next encryption. And we want to, so we're going to loop, right? While, we're going to say while previous encryption is not equal to next encryption, and we're going to look at the bytes of both. Then we're going to do stuff, but then we have to set next encryption every time to be like, I'm trying to think of a way to say this. Like, basically, I'm going to try and shortcut one step here, where now every time before I compare, so at the end of this, then I have to set next encryption. I'll do the next encryption. Then I set previous encryption to what next encryption was, or I'm doing that backwards. Oh, so I set previous encryption. So actually I should use current. So we want to compare previous to current, and then at the end I have to set previous equals to current, and then I'll get current equals next. But basically just because I want to show something different, because I feel obligated to try and teach something, and I feel like I haven't been doing the best job. We're going to use what's called a walrus operator, which is basically like we're going to compare and assign in the same thing, which actually is like really helpful. This might be a shoehorned example for that, but let's do, we're going to get next encryption, and we're going to use the walrus operator. And what's that saying is, it's saying to go ahead and set, we're like assigning this variable basically at the same time we're going to try and compare it to. So like, all right, let me write it out, and then maybe it'll make, so I'm going to say, what do we want that to be? We want that to be equal to the encryption of feed, and we want it to be just that block. And then we're going to compare that to while it's not equal to previous encryption. So basically I'm setting it in the same spot I'm comparing it to, and that's probably not the best example for that because it's just so long, so it kind of makes it ugly. It would actually look better the way I described it before, where we just have an extra line of code at the end and we're setting next or current to previous, and you know what I mean. But anyway, this is a walrus operator. It's when you're setting it at the same time you're kind of declaring it. So you're declaring it like you don't declare really in Python, but like we haven't used it before, and so we're declaring it and setting it to a value all at the same time. So while those two are not equal, that means we need to keep sticking A's in. And then I need to set previous to what next. So actually, instead of next, I should call it current. Current encryption isn't equal to the previous encryption. Then previous encryption equals current encryption. And then, so this will keep going. It's adding A's until at one point the current encryption no longer, or the current encryption actually equals that block. The current encryption equals that block of the previous one. And then that means we have 1A too many. Like if it took 10 A's to fill that block, this while will not evaluate as true when we have 11 A's. So we can then just return, and we want the prefix size, so we want the we started on the beginning of that block, so we want the end of that block minus the length of our feed, but we had 1A too many, so we want to subtract 1 from that. So if we were, for example, say, what have I been using, 38, so say we were 6 bytes, prefix ended 6 bytes into some new block. So we're starting on index 32, so that means that block is going to end on 48, and then however many A's we added minus 1, so we ended up on our 11th A, we broke out, so we need 10 A's, so 48 minus 10 gets us to that 38, so then we know there is 38 bytes of prefix. And I think we're good now, yeah? Prefix size, we had our prefix fill, we're ceiling dividing minus, that's how many we need to fill it with. All right, let's just see. Start running through the errors now. 3, what are we on? Challenge 14. Oh, did we not import that? Oh, yes, we did. Line 21. Oracle. Oh. Must have just been holding down the 0 for some reason. Weird. Name add is not defined. Oh, I called it added. Oh, sweet. Only a couple errors. Yeah, so we already know that was what it was from the previous one. Let's go ahead and let's, since we're getting random, let's see, I want to know how long it actually is. So let's just for giggles, actual prefix. And then we'll see, like, really if I were gonna like test this and make sure we want to look for probably like edge cases, like would this work if we had no, it should still work if we had no bytes in front, but then the other one that might mess it up is if we had exactly a block size of bytes. So I just wanted to run it a couple times and see. I'm printing it out. I want the length. Oops. So that's 2. When we have 26, it works. Let's just go ahead and actually let's test it. I want to make sure it works, like if we had exactly a block size. I mean, it should, but that would be like one of the test cases I definitely want to check. Yeah. So, and then like, will it work if we have a whole bunch? I mean, that shouldn't matter. Yeah, so we're pretty good there. Make sure it still works. So yeah, that's challenge 14 down. So now oh, okay. This one will be super easy because we already wrote way back many hours ago. We wrote our own padding function. So this one will be really simple. challenge15.py, and it wants us to, so from utils padding import, we'll import on pad, if main equals name, we get our main, and then what did they gave us? The string has valid padding and produces, and then we want to check that those are invalid. So we're going to do our ghetto testing. So then our answer should be ice baby. The result is what we get when we unpad test to. I don't want to have to import something, so we'll just do that. And then we'll do our fancy print. Get it correct. Answer equals result. And then we'll print out the result just in case we foobarred it. So we can see what it is. And then they want us to do a couple wrong ones and make sure it doesn't do it. So we're going to, and I don't think we've done this yet either, we'll do some try catching. So if you're going to do something that throws an error, use what's, I guess in Python it's try except, but in my head I always think of it as try catch block. So we're going to unpad that string to 16, and if there is an error, like if we were to run this, like here, if we run it without this, and let's say the other one we wanted to do, we also wanted to test, we need these to be bytes. This one, it was 1, 2, 3, 4. Like if we were just to run that, it's going to crash because these are going to raise an error. We're going to get a value error, and program's going to stop right here, and it's never even going to go to anything after that. Oops. Yeah, so we got a value error, not valid padding. So the way to do that is to have it so you can do things in your code that might potentially raise errors, and you don't want your code to halt on an error. You do try. So we're going to try to do this, and we will accept. Now you can, like if we just had it like that, it'll, like, so no, if we said there. So like now it'll catch like every exception, and so like before we crapped out on line 10, so now it should. Now it'll get an exception, and it'll go ahead and evaluate this one. But what I want to show is, wait, before it was, so we should crap out on line 15. Line 10 in unpad. So it's line 15 in main, and before it was line 10 in main. Okay. But really, it's kind of better practice to, like, if we know what kind of error, like we know if this doesn't work, it's because we're going to get a value error. You only want to try and catch like the minimum amount of errors, because if we just let it go, we don't care what the error is, like we're missing out potentially on, like, maybe this doesn't work, not because it's like the value error we think, maybe there's some other thing that breaks. So we're just going to catch the value error, and we're going to catch it as error, and then we're going to print it out to make sure it is what we think it is, and then we would do the same thing here. We're going to accept value error as error, So now the code should run like what? Now we should get to that. That should print because the errors aren't going to crash our program. But it will print out the errors so that we know what they were. Yeah, so not valid padding, and then it made it to that section. So yeah, boom, challenge 15 done. So now we are on the final one. Where's my tab here? There we go. Okay, bit flipping. So here we, oops. Okay, so this will be another fun one. So we're kind of going to do like sort of like how we did earlier where we had the like, you know, some make-believe service, and we are going to have controlled data that's basically going to be in between these, and we're not allowed to use the semicolon or the equal sign, and we want to try and get the same situation, right, where we can get some kind of string in there where it says, what are we going for? Admin equals true. So the way we did it last time with the ECB was we kind of like manipulated things to get blocks that we wanted to use, and then we just cut and pasted those blocks. Well, with CBC, like if we remember, we're not really going to be able to do that because every single time the ciphertext blocks are different. So we can't just line stuff up and copy and paste. But what we can do is we see over here. So if we encrypt something, and then we see over here where we decrypt, what comes out of the encryption, what comes out of the AES block is called the key stream, and it gets XORed with the previous block of ciphertext, and then that makes plain text. Well, technically, if we can tell what comes out of here, we could XOR it with whatever we wanted to make it create whatever we wanted the plain text to say here. Now that'll mean that this ciphertext, when it gets run through encrypted, it's just going to come out garbage. But when that comes forward to this one, we can make this plain text say whatever we want. So depending on how, like in this realm of like this service we're building or whatever, depending on how it handles the entire decrypted plain text, if it's just checking to look for, you know, if admin equals true, and it doesn't matter, you know, if this stuff here is garbage, we can in effect control whatever we want. So that's called bit flipping, because we're going to change bits in this ciphertext, because then we can control what this plain text gets decoded as. So I was going to bring, maybe we'll just start on it, and then if I need to, I can draw some diagrams or something. So we are on challenge, what is this, 15, 16. Now, I don't think we're going to be able to use, yeah, because our services aren't really the same. But we'll do the same way we did before, where we'll basically just make, is it lowercase? Some service. And then we'll have, sheesh, what's my brain doing? We'll have an init. And then this is how we'll make sure the key is the same every time. So we won't know what it is, but it'll be random. And we won't need to know what it is to flip what we want in the other ciphertext. So we're going to need say yes. Do some padding. We're definitely going to need our XORing. Random. And then, so our service, let's see, it needed, oops. It's going to take an arbitrary input string, prepend, append, and then pad out, encrypt it, and then it's going to give that to us. So just like how before the other service gave us the encryption, this one will do the same. And then the second one is going to decrypt it and look for is admin. So we'll have basically kind of like the similar, what did I call those in the other ones? Encrypt profile, decrypt profile. Although the other one we were decrypting it to an object. So, okay, let's just do, all right, we'll have two functions. We'll have encrypt user data, and it'll take a string, and it's gonna just return bytes. And again, like in real life, our service wouldn't be returning bytes because if we're doing it over the internet or whatever, that would be no bueno, but we'll just make it easier on ourselves. And then we'll have another function that decrypts user data. Basically, since we're just trying to check to see if we're admin, let's just make it is admin. So we'll have a function where we'll give them a ciphertext, and the service will be like, yep, you're admin, or nope, you're not an admin. So we'll say encrypted. We'll just call it encrypted data. And we'll do bytes, even though, again, like that would not be good over various protocols. And then we're going to need to parse this stuff. So they're going to prepend, append. We need to make sure you can't use equals or so let's have a parse user data function that will take data of string and it'll return bytes. And here, instead of like last time, we just made it so you couldn't use those at all because it would screw up how we were going to convert that to an object. Since here we're not actually converting to an object, we are just, where is it? We're looking for a specific string. Like we can look for that, or like, we could carve it up and, do it like how we did the parameters before, but we're just going to do it this way to make it easier on ourselves. So we can just escape it this time. So data, we're going to replace the semicolon. We'll just escape it. And I have double backslashes because a single backslash is an escape character, and that's not anything. So I'm escaping it to say, no, I actually literally want a backslash and then a semicolon. And then we're also going to replace the equals sign with the same thing, slash equals. And then we can so then data will equal that string plus our data plus that string. And this here is Well, it's highlighted because that would also be like a, what is it? UTF-16, I don't know. But that's basically just URL encoding. %20 is a space. So it's cooking space MCs space like, etc. And then we will just return, since we need it in bytes, we'll return that string encoded. So we're encrypting user data. We are going to parse that data, and I guess we could just encrypt it right here. What I'm thinking is, because we're using CBC mode, and if we just like create the cipher, with our AES up here, it'll get created with a random IV, but that IV will never change, which doesn't really matter for our purposes. But every time you encrypt something, you should have a different IV. So actually, let's just we'll write separate encrypt and decrypt functions, just to make it a little cleaner in my head. And then we'll have and then in each one of those we will do equals new self.key, because it's the same key every time. And then it is AES mode CBC. And then we don't provide an IV, it'll just create a random one, which is fine with us. And then we will return encrypted data. And then for decrypt, actually let's take we'll also need an IV. And then we will key, the data, and the IV. Oh wait, not give it the data, we give it the mode. AES dot mode CBC. And here we will decrypt the data, but we also need to unpad it. Okay, and then what we can do here then in encrypt user data, so we'll parse the data, and parsing it will escape the characters we don't want. It'll prepend and append all the stuff, so we'll call it final data as that, and then we will just return we're going to encrypt we need to pad it, we need to pad final data to the AES block size. We're encrypting that, and that is what we're returning. So then for isAdmin, we can, well, I'll go ahead and put it on more than one line just to make it kind of clear. So like how I said, our AES just prepend, when it encrypts something, it prepends the IV to the ciphertext. So the first 16 bytes of the encrypted data we're going to give it back is going to be the IV. So the first 16 bytes will be the IV, and then the ciphertext will be everything after that. And then we will, the user data is what happens when we decrypt that. So user decrypt the ciphertext and the IV, and then we are going to return whether or not admin equals true is in user data. So if this string is found in the data after it decrypts it, the service is going to grant us admin privileges, and I believe that's all we need to do. Just return true or false for the string. We cannot provide it what we're looking for because we're escaping those characters. Okay. So now we can actually go about doing the fun stuff. So if okay, so I'm going to actually bring my thingamajigger up here because I need to plot this out. So we have this much, then how long is this? So we have whatever this is. Let's see how long that is. That was nice of them. It's exactly 2 blocks long. So we start injecting our user input on the start of a block, which is perfect. So the one block ends with, here, I'm going to write it down while I can see it. User data equals, and that's where the block ends. And then we get whatever we want, and then the next block starts out with, or not the next block, but then like this, what comes after that is going to be a semicolon and then comment. So, okay. Excuse me. Okay, so presumably, like, we would just, user data is just going to be, you know, a string of whatever, and the way this program is like, oh, okay, yeah, we'll just let the user input that, and then we'll go back about doing all our other stuff. And it's nice of them because this here starts on a block. So what do we know we need? We know we want somehow we want to get the string of admin equals true in this block here. We can't copy and paste blocks. We have to like figure out exactly how to get it here in a block. So how many bytes is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 bytes. But we can actually use this semicolon. So we'll line these 2 semicolons. So what I'm thinking here is if we actually get it to end here. So if we make this an actual whole block, we'll start out exactly how we want. So we just need to make it take up enough room that then we'll cheat and we'll use that semicolon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we've got 11 bytes here. And what we're going to do, since we can flip, we can control specific things, right? We know we're actually allowed to write admin. We can't write equals. So let's just put a big X there. But we can write true. And then we're going to use their semicolon from there, so we don't care. So we just have another byte here that we can't control. So I said that was 11. So we need 4 bytes of anything we want here. So let's just put blah. B-L-A-H. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, okay. So, oh yeah, because it was 12, 11, so we need 5 bytes. So we'll just do blah. So when it ends up, if we can flip these, we want to flip this, make this a semicolon and this an equal sign. So in this previous block up here, somewhere in that ciphertext, there's two bytes we're going to have to change. We're going to have to flip some bits in those bytes. And then if we do that, then what would happen is we're going to end up getting in this string, it'll be blah admin equals true. And then the start of the next block will be all that stuff. So we'll get that string that we were looking for. And then again, so if it's still not clear, oops. So we said it was exactly 2 blocks. So it's 2 blocks of their stuff. And then our third block is going to be when we first make it, here's where we're going to put blah x admin x true. And we're going to get the ciphertext all that back. But then what we're going to do is we're going to change. Here's what it should be. We're going to actually change 2 positions in there to something else, so that when what the ciphertext was for the third block, when it gets encrypted, we'll know the key stream for that, and then we can, when it gets XORed versus that, we can control what that is because we give this service the ciphertext to decrypt. So we'll flip 2 positions in here, and then when it gets XORed versus that, it'll come out to what we said we wanted it to be, which was this right here. And then when it checks for that string, it will find it. So if we go back to the coding now, so let's see how we want to do this here. So we'll have our service is some service. And then we'll call our dummy text, what did we say? Blah x admin x true. And what we want to get is blah semicolon admin equals true. So from our service, we will get the encrypted dummy text. And that is going to be service when we call the encrypt user data function and we give it dummy. Now we have these now with our dummy text. So we have our dummy block with what we want, and so we know what it should sit. Basically, we don't know what the key is, but we can figure out what the key stream that comes out of here, right? Because we know what the plain text should be. We know what it is if it decrypts right. We know what the previous ciphertext block is. So because of the way XOR works, we can XOR the plain text with the ciphertext, and we'll get the bytes that come out of AES. And then knowing those bytes, now we'll know what to XOR to get the plain text we want. Hopefully that makes sense. So we need to figure out, so we've got dummy. We need to figure out what the key stream is. And then, so let's get a flipped block. So the flipped block will equal, we'll have a bit flip function that will take what we want it to be, what it actually is, and then the cipher, because we need three things. We need what the ciphertext actually is, we need what the plain text actually is, and we need what we want the plain text to be. So we need the target, the dummy, and then we need to give it the that ciphertext. So which was our encrypted dummy, and it's the third block. So we'll give it bytes 32 to 48, and then these are strings. Is there any reason? Oh yeah, because we're gonna give it strings. So we'll just turn them to bytes here because our function takes bytes. Our bit flip function is gonna take bytes. And then once we have the flipped block, then what we do is we're going to, let's go ahead and actually, for clarity, we'll say flipped encryption is going to be the first two blocks of our encrypted dummy. Or no, it should be the first block. Let me think. So we said that was exactly 2, and then we're gonna do it. So let me look at this diagram again. So that's, and then that gets XORed with our plain text to create that. So we're going to have those two blocks. Oh wait, but it's, yeah, we want to flip the second block. Okay, so it should be, right, then I gave it the wrong flip block then. We know what the target is, what it actually is, and yeah, why did we give it, we don't want to give it the third block. So, okay. I'm getting confused. Our plain text is our dummy, and then we will have what our actual, so what it decrypts to. So when we go to flip it, we need to know, we need to have this ciphertext, this, the actual plain text, because to get the key stream, we need what it actually decrypts to, what that second block was, and then we also need what the target is. So yeah, we don't need the, okay. So we will give it the second block of the encrypted dummy, because that's the one we need that to get the key stream. Here, maybe it'll help me if I just write the bit flip function. So we want we'll say our target decryption. We'll want our current decryption, and then that'll be bytes, and then we want the previous ciphertext. That'll be in bytes, and we're going to dump everything back out in bytes. Now, to get the key stream, we are going to, let's see, key stream is going to be the plain text XORed with the previous ciphertext is what went in, so that's what comes out. So we want a plain text. We want to XOR what it currently is with the previous ciphertext, and that will give us the key stream. So key stream equals the XOR of the current decryption and the previous, I should call it previous block maybe. And then we want that new block to be, so now we know what the key stream is. Now if we take that key stream and we XOR it with what we want the plain text to be, that will tell us what we need to make the previous block. Oops. So we can say our new previous ciphertext equals XOR of what we want it to be and the key stream. And then we are going to return the new previous ciphertext. Okay, so we're going to give it what we want it to be, what it is. Yeah, because this is a full block. So what it is, what we want it to be, and the previous ciphertext, which is the encrypted dummy 16 to 32. And then our flipped encryption, we want to give it we can give it the real first block. So that will be plus the flipped block plus everything after that. Yeah, so we have our encrypted block. The new block we changed because we changed this block. It's going to end up being garbage here, which is okay. And then that block goes into there because we start on 1 block, 2 block, 3 block. Okay. So then now we can check for service dot, we call it isAdmin, and we will give it our flipped encryption. And then now we can do our cheesy print statement. Admin. All right. Let's see if it works. 3. Challenge, what are we on? 16. Some service object has no attribute encrypted. Oh, where did I call it? Encrypted data. Encrypt user data. Unpaid. Let's see, where do I have that? Line 36. My brain is getting pretty fried. No, we're not admin. Okay, what did we do wrong here? Let's see what the user data is. User data. User data. Oh, okay, so we're not flipping it correctly. All right, where's my logic going wrong then? And our first, oh, so that's the IV. User. Yeah, it makes sense that second part. Oh, okay, that's, all right. Okay, here's where I'm going wrong. We have to remember that what we get back is so like when we encrypt, the IV is prepended to everything. So we have to shift everything up by 1 because encrypted dummy is actually 14 or 16 bytes of IV and then the ciphertext. So it's really 32 to 48. And we give it the 32, and then here would be 48. So now yeah, because I probably should have done something so that I don't make that dumb mistake, so that I don't know, you could have encryption give you back IV, but I think it's just, I don't know. My brain's melted from many hours of this now. So this should be good now, I think, because we have the IV. Okay. Let's go and try it. Okay, it did work. So but why is... Oh, because we're already taking the IV out. So that actually wasn't the IV. That's just the garbled block. Okay. So you can see here that the first block comes out fine. So like when we decrypt it, we screwed with this one, right? So the first block plain text comes out fine, right? We got our comment cooking, comment 1 equals cooking. And then we change this. So it's all going to be garbled now. It's not going to be what it was. So you get all this garbage. But then we go back to where we're actually getting stuff, because we changed this one and it changed that plain text. And then since that's the only thing we changed, everything else down the line will stay the same, because this ciphertext, which we didn't touch, encrypts the next block, blah, 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 blah. But you'll notice that there's a bunch of random gibberish in what the service should be expecting data in. So depending on how the back end is parsing data, like for example, if let's say it's not looking for, let's do it this way. So user data, let's say in the back end, I'll just comment this out right now. It wants it as a string, and then it's going to check if admin equals true is in that user data. Now this is not going to run because there's non-printable characters in here. So now all of a sudden the service, shits the bed and their code stops working and, there's problems. I can show you what it's doing. So like if we're going to code it to ASCII and it's replace. Oh, I want to print it again. See, we've got over all these here. Those are all unprintable characters. So there's a lot of ways for, people writing the code and the developers to make sure that like this kind of attack doesn't happen. And there's also a lot of ways where they'll figure it out, even if they weren't planning for it, to try and stop it, because you end up, depending on how everything's being handled in the back end, you end up with a block of utter gibberish. So that should be all of them. And then that's kind of what it talks about here. So like produces 1-bit error. So why does CPC mode have this property? So that it has that property because like we talked about earlier, like that's kind of how you ensure you don't get the problems you have with ECB, is a change in a block propagates through all the rest of the blocks. Although in this case, it's just propagating the next block. But it still shows that when we tampered with the ciphertext, it was pretty easy to detect that happened. I believe that is all of them. Yep, so that's all of them. So I don't know if you made it this far through these many hours, or even if you just watched part of it because there was a particular problem you want. Like, I really hope that I was able to like explain something and that you got something out of this. And hopefully I keep getting better at making these. Maybe they'll be shorter in the future, or maybe I'll split them up. I don't know. Anyway, have a good day, and thank you very much if you watch this.